Good morning everyone. So welcome, good morning and welcome to the second day of the EASA AI Days. So we will have a big program also today. So thanks for all the people that were yesterday with us, and I think we had very nice exchanges, very nice also a get-together evening. We could pursue the discussions. And now we will enter into, I would say, research. One of the research measures we started from EASA side, knowing where we started from the learning assurance and trying to dig into the tough topics. So the great thing, we have the full MLEAP team with us today. From Airbus Protect, LNE and Numalis. We have also Thierry Racot, special guest CEO of Airbus Protect, and thank you to all of you for the support you gave to this project as a consortium. It was a great time and work together, but you will see that all across the day. The results are good, are promising, are giving perspectives also on where we still need to twist and research. Okay, with that, maybe just a quick note before going to the lunch break. We will try to go up on the roof top of the EASA to take a group picture, which we didn't do yesterday, but we have most of the people stayed for the 2 days, so that's great. So let's try to do a group picture before we enter the lunch break. And with that, I will directly give the floor to Mathieu Rochambeau from Airbus Protect, who will be our host and for today. Thank you.
Thank you, Guillaume, for the introduction. So good morning, everyone. Welcome, and thank you for joining us today for the second and last day of the EASA AI Days edition 2024. My name is Mathieu Rochambeau. I am working at Airbus Protect. I am the communication officer in the MLEAP project, and I will be today's master of ceremony. So I'm really glad to be here with you today, seeing this room full, and even a great presence online. So that's really awesome, and thank you for all being here today. So today, as Guillaume said, it will be a full day dedicated to the MLEAP project. So the MLEAP team will be giving its final presentation after 2 years of work research. So the MLEAP team will give a deep and insightful presentation about the MLEAP project and the 2-year work results, and also the main outcomes of the project. So as I said, we will have the full day to do so. So we will have plenty of time to cover the various aspects of the project, and also enough time for questions and answers. Before we get started, I really would like to also thank the EASA for having us here 2 years in a row during the EASA AI Days to talk about the great project that is MLEAP. And special thanks to Guillaume and his team. So first off, for setting up this great 2-day event, but overall for the great collaboration that has been going on to make the MLEAP project happen and a great success. So thank you, Guillaume. So about MLEAP. So MLEAP, it stands for Machine Learning Application Approval. This is an R&D project that deals with artificial intelligence and AI. So the project was founded by Horizon Europe, a research and innovation program, and was initiated by EASA as part of the AI Roadmap. So Airbus Protect has been project leader and technical leader of MLEAP, and alongside with us to work on the 3 main tasks of the project, we are partners with 2 French companies that are here with us today, LNE and Numalis. So just a quick recap about the 3 main tasks of the project. So the first one is about completeness and representativeness. The second one is about generalization guarantees for machine learning and deep learning models. And the third one is about robustness and stability. But the EASA will soon give more details about what the project MLEAP is about. So before we kick off with the presentation, let's have a look at the agenda of today. So we'll start off with the introduction of the MLEAP project and the partners. Then we'll go over with the presentation of the use cases. Then we will have the 3 main parts with the presentation of the outcome and recommendations of task 1, 2, and the task 3. Then we'll have the general conclusion and recommendation from the MLEAP consortium. Then we will continue with the EASA perspective on MLEAP takeaways, and then we will end this 2-day event with the conclusion of the EASA AI Days 2024. So as you can see, in between the main presentation, we have inserted a 20-minute question and answer sessions. So it will give us plenty of time to answer the different questions that you may have. So to do that, it's quite simple. It's like we did yesterday. We will use Slido. So we just have to scan the QR code that will be shortly displayed on the screen and enter the password, and feel free to directly type and address the question. And like I said, we have plenty of time to answer most of them. So please feel free to address them. So, is there any questions? If not, I suggest we get started with the presentation. So again, thank you all for being here, either physically with us in the room or virtually, and have a good one, and I hope that we'll enjoy this conference. So let's start by who is who within the consortium. So as you know, EASA is the contracting authority of MLEAP. Airbus Protect is technical leader and project leader and also owner of the task 2. LNE is owner of task 1, and Numalis is owner of task 3. So just quickly, let's just have a quick introduction about who is who within the consortium. So let's start with LNE. LNE is a French state-owned institution tasked with the coordination of the French metrology and the testing and certification of various products, including AI systems. So I will not go over the EASA. So Numalis is a French deep tech expert in formal methods, providing industry state-of-the-art and technical solutions for AI explainability and validation. And Airbus Protect, so it is a subsidiary of Airbus that is specialized in risk management and is working on three main domains, which are safety, sustainability, and cybersecurity. So I will hand over to you, Xavier, to present the introduction of the MLEAP project. Yeah, so floor is yours.
Thank you, Mathieu. And yes, just to give it a start, so the team on EASA side was Xavier was the technical lead, so he really did most of the job, and I was contributing together with François Triboulet to some of the tasks and technical work. So that's really you have the full team today. You can engage and network anytime at the breaks or through the Slido questions. I will repeat again, something that we said yesterday, but maybe for online participants that would have joined only for the MLEAP day, we all drive the activity on AI from EASA side based on this roadmap 2.0. That's a slide I explained yesterday. Maybe not going on to all the details, but really focusing on this deliverable of phase 1, which was the exploration phase, which is the EASA AI concept paper issue 2. That was our really reference point, or that is our reference point to go in the consolidation phase 2 into rulemaking, into further exploration, as we said yesterday, at length on level 3. And on the way, we have a building block, AI assurance, actually tailored to learning assurance so far in the concept paper, which requires a certain, let's say, novel elements of process objective from a process objective perspective, from a development assurance perspective, if we take it from a large perspective. And this is something we saw. We have a couple of objectives that are through the use cases we investigate with industry are challenging, are really difficult. And if we turn to researchers and we look at what exists today in terms of research on statistical learning theory, etc., we see that there is a real challenge that is still up on the radar, like for generalization capabilities, quantifiable. It's a big word, quantifiable, but that's really important. I mean, if we go high up in the criticality of applications, that's guarantees that we will look for. And this is something we have identified on 3 topics that Xavier will really show in more details. And we started this MLEAP with the 3 tasks in order to investigate this aspect. So the concept paper is definitely our main reference. But the MLEAP report that you could see coming is a comprehensive report of 500 pages with also an executive summary so that people can read it also in a quicker way. But the 500 pages report is definitely another piece of gold for us to enter the consolidation phase and will help a lot. From that perspective, another slide you saw yesterday presented by Giovanni for the use cases, but still reinforcing this message. It's a collaboration, a collaborative effort that we are undergoing. EASA alone would not dare or would not manage to create a concept paper at the level that we reached so far. And it was really based on a lot of discussion, a lot of interaction with all our stakeholders. You see many of them here on the screen, but those use cases are feeding both the EASA thinking and the working group that was presented yesterday by Christophe. We have this effort going in parallel, and that's great because that creates really this interaction in a triangular way. And then the big message that we didn't insist yesterday, but today is really about research. Whenever we see we are missing something in this capability of, let's say, authority, industry, and working group to come up with the means of compliance and the anticipation of means of compliance to the objectives of the learning assurance process, then we turn to research. And we will do the same for human factors in some time because there are a lot of challenges. But for today, with MLEAP, we focus on learning assurance in the block of AI assurance. And we have other projects going on. MLEAP is not the only one. We have CESAR 3 projects. We have some LUFO projects we are following. So there are several projects and frameworks that brings us capabilities to engage. But MLEAP was, let's say, tailor-made for the need that we have from an AI program and an AI roadmap perspective. So very, very happy and grateful to have the consortium with us to report on that. And with that, I will pass the floor to you, Xavier.
Thank you, Guillaume. First of all, thank you everyone for being so many here in Cologne. Maybe we won't see this slide, I promise, many times today, but I think we've presented it many times, but to have some understanding of where we are in MLEAP, let me quickly go over the building block and explaining what we are doing in those building block and where is MLEAP going to help us. So as you know at this stage, the EASA concept paper that was deliverable from phase 1 is structured along 4 building blocks. Each of these building blocks has a set of objectives, and in some cases, we have identified some anticipated means of compliance. The first building block is the AI trustworthiness analysis. That is as a classical building block with a set of objectives consisting in characterizing the AI, making some safety assessment, some cybersecurity assessment, as well as the ethics that was discussed at length yesterday. Then we move into the 3 technical yellow blocks, the AI assurance, the human factor for AI, and the AI safety risk mitigation. So AI assurance is divided in 2 main parts. The first part is a learning assurance, which is the adaptation of development assurance techniques, so VNV system engineering methods used in aviation, to a learning process. And this is where the W-shaped process that was designed a couple of years ago as that is one of the output of the IPC's CODAN comes from. We have also in the AI assurance block the explainability for development and post-operation. And then we have 2 other building blocks, the human factor for AI that was extensively reworked for the issue 2 of the concept paper, divided now in 3 parts: operational explainability, human AI teaming, that was one of the areas where we spent a lot of time beginning of this year, and modality of interaction. And the very last building block is a safety risk mitigation that is foreseen as the last part of the last set of objectives that we can use to show compliance in case full compliance cannot be achieved on AI assurance or human factor. So it's a complementary set of objectives that aims at completing the compliance demonstration. It's a quite complete set of objectives, and actually MLEAP is focusing on the W-shaped process. And actually, it's not looking at all the objectives of the W-shaped process. It's really looking at key objectives, where at the time, when we published the first issue of the concept paper, we identified some technical challenge. So 2 years and 2.5 years ago, I would say, we started drafting the tender, having in mind that we needed, in some area, to identify means of compliance. We gave us a timeline of 2 years, and Horizon Europe supported this approach by funding the project and funding the project up to 1.5 million euro. After tender, the tender was quite successful, and we selected an ad hoc research consortium, as Mathieu explained, led by Airbus Protect, with LNE and Numalis. What we ask in this tender was to look at 3 technical tasks. The first one being related to data completeness and representativeness. The reason for that is that we wanted to focus on where the cost and the complexity is, and machine learning is about, to simplify, is about learning the pattern within the data, but to do it properly, it's essential for safety critical application that the set of data is complete and representative. And at the time, one of the roadblock of challenge we identified was that there were not so many tools or methods to show that these properties properly achieved. So this is why we designed the first task on data. There was also a second challenge that was brought to our attention in the community, in the working group, related to the need to do trade-off between representativeness and diversity. And this is why in the first part of the project, these two properties, we spent some time characterizing these two properties and looking at how to achieve the right balance. On one hand, the data set should be representative. On the other hand, we want the model to learn from the most critical case or from the edge cases. So there is here a balance that needs to be properly managed. And the two objectives that are related, the three objectives that are related to this first task are DA03, 04, and DM07. So we slightly changed the number of the objectives in the concept paper issue 2, but these are the new numbers. Mainly DO4 is requesting to define some data quality requirement, taking into account completeness and representativeness, and DM07 is asking to verify the data quality requirement. So that was for task 1 that was executed by LNE. The second technical axis was generalization. Not only we want a model that works well in the lab, but the paying passenger are also quite interesting in having applications that work well in the field on unseen data. So at the time, there were a number of promising papers that were available, and so we used MLEAP to gain a better understanding of what could be done on an industrial project on generalization, asking in the tender to look at qualitative method and possible protocol and strategy that could be used all along the project to improve generalization capabilities. Having in mind constraints in terms of data quality and volume, and looking at whether quantifiable guarantees could be achieved on let's say, on industrial projects. As Guillaume mentioned, quantifiable guarantees may not be the roadblock for the very first applications with very low criticality, but as we look at more critical application, as we look forward to autonomy or safety critical or application that could result in accident or unsafe conditions, this is one aspect where we identified the need to understand better what was the state of the art, what could be done, and whether the technology was mature enough. There is a set of objectives related to generalization guarantee. I mean, I have listed 5 on this slide. We will go into the details later on, but it's mainly in the LM part of the concept paper. And there is a link done to a safety assessment in the concept paper to use some of the LM objective demonstration in the safety case. This part of the project was executed by Airbus Protect, which brings me to the third task that has to do with robustness. At the time we initiated the tender, we had worked already for some time on this concept. We had the concept paper, but we had only 3 IPCs, the 2 Codans paper, mainly the Codan 1 that was looking at the robustness aspect. Codan 2 was following up on some aspect not covered fully on Codan 1. The 2 Codans paper have been helping us over the last 4 years in steering technical discussions. And they've been developed with the industry, with Dedalien. And we wanted to use this tender to compare the approach that was discussed in the IPC with what was being drafted or prepared in the ISO. That was one of the first subtasks we had in this part of the project. And then this task was also designed to look at the benefit of formal method. We were in the process of initiating with Collins Aerospace Formula IPC that was finished last year. And this task is the follow-up of Formula on assessing how we can use formal method in compliance demonstration for AI application. But these are not the only approaches that were considered. Actually, we have looked at 3 families of methods: empirical, that relies a lot on expert knowledge; statistical methods that relies on making a test on a property that you can, or assessing a property with a test that you can, performing a test on a property that you can assess with a certain confidence. And then formal method, where on a given input, for a given input space, a certain property is formally demonstrated. This part of the project was allocated to Numalis, that is an actor that is specialized well, in several domains, but formal method is one of their area of expertise. The 3 or the 4 objectives that are related to this task are LM02, 11, 12, and 13, that basically require to assess the stability of the algorithm, of the model, and to assess it in the first part of the project, of the development, the validation part, and then verify it later on with LM13. And there was also a 4th axis in this project that had to do with getting EASA team familiar with complex aviation use cases. So this is why for this R&D project, unlike what we may have done on other projects, we have asked for strong provision to access models and data produced as part of the project. We were both relying on one hand on public data, so that on what we've called toy use case later on in this presentation, so that if people interested in the research want to duplicate or go further on some of the methods and tools, they can do. But we also ask in the contract for the consortium to look at complex aviation use cases so that we can actually validate the method on industrial, on credible application. And this is why we ended up testing the project on 3 complex aviation use cases that we'll detail later on. And then we used also this 2 years project to get feedback from the various stakeholders. And this is why we have organized or being part of so many conferences to get your feedback and steer along the way the project towards the direction that were of interest. There were a number of cases where particular methods were highlighted to us and were accounted for in the project. We are now done with this project. It was finalized a couple of weeks ago. We've published the final report. We've done one single detailed deliverable, that is the final public report, available on our website. It's 500 pages long. So maybe if you want to know more about the report, you may start with the detailed executive summary, that is only 20 pages. And I invite you to contact us in case you have questions, remarks about the report. We had a number of feedback last year on the interim report that we have accounted for. And so if you spot some issue or if you want further information, don't hesitate to contact us. We have contact information for the project at the end of the report, and we would be happy to look at any comment you have. And if needed, we may update as necessary the report. With this, I will hand over to Tidri for the presentation of the method.
Thank you, Xavier. So, hi everyone. I'm Tidri Belkacem, Innovation Manager of the Digital Department in Airbus Protect and the Technical Advisor of MLEAP project. So, at this part, I will start presenting first the objectives of the MLEAP project from our perspective on the technical part. Starting from the analysis of the statement of the call for tendering, in fact, starting from this one, and the analysis of our engagement toward the project and the EASA expectations. So we have identified the two main objectives that we think are very important to understand and to highlight from the beginning of the project. This includes the analysis of the objectives of the AI roadmap and how we can identify means to streamline the this roadmap and give some information and recommendation about how to reach the means of compliance and verify them for the different AI developers and operators. And the second part, which focuses more on the applicative analysis of real use cases, real aviation use cases that are related to safety critical systems. So based on these two main big parts, we have set the development roadmap toward reaching these objectives. And then we had as a final objective of the project to put all the conclusions that we had together in order to provide an end-to-end pipeline that enables to follow the different statements and so let's say the different recommendation, the methods and the tools that we will be recommending. So starting from the analysis about task 1, here I'm not gonna detail the complete W-shaped learning process. I think it's already explained in the good way by the EASA yesterday and in this morning introduction. So here we identified all the parts and the steps that should be and can be also covered by the scope of task 1 that focuses on the data management, and identified the data management and all the data related objectives from the EASA concept paper and the roadmap for level 1 and 2 AI. So as you can see, it's really located on the highlighted parts with the green boxes. And then the same exercise for task 2, where we show here at the same time the learning management parts, where the objectives of the learning management from the concept paper can be and should be also covered by task 2, but not only, of course. So you will see on the presentation of today that all the different parts are very significant for the learning management and the learning verification. For task 3, where the same exercise again was done in order to identify at each step what should be done, what needs to be verified, in order to say that at the ending of the development process, we have a model where the learning have been verified and validated, and the model is ready to go for the implementation. So the roadmap of our work was as follows. So starting from the analysis of the state-of-the-art and the MLEAP aviation use cases as any research project. So starting from the analysis of the existing elements, what we can bring as new, or how we can reuse the existing materials from the state-of-the-art, from all the open source materials, and what we have internally inside the consortium, what we can bring for the project in order to meet each of the objectives. So at this step, we identified sets of methods and sets of limitations and missing parts in the state-of-the-art in order to reach the objectives of the MLEAP, which targets more the having the projects finalized, having the AI modules developed, validated, and put into implementation for the target system without having some impacts on several parts of the system. And then in the second part, and the second big step of the project, all the selected methods have been subject of first experimental results using first experimental analysis, let's say, using the sets of toy use cases. You will see that there have been too many toy use cases used in order to first analyze the applicability and the behavior of the selected methods in some similar use cases to the ones targeted by the MLEAP project for the aviation real use cases. And at this stage, so the generic method for the development have been initiated, and first results have been developed, where on the first public report of MLEAP, you have seen already some first results and the perspective for these three big steps, where all the methods selected, the first conclusions, so the first, let's say, assessment of the methods and results have been verified on the real aviation use cases, comparing the methods and seeing how we can reach and meet the objectives from the learning management, the data management, the learning verification, and also finalize the complete pipeline that you can see here. So this afternoon, this complete pipeline will be detailed and presented in detail. So I highly recommend you stay here for the whole of the day in order to see more about what we can do at each step. And these generic pipeline that have been developed inside the project have been used in order to, let's say, streamline this roadmap by the EASA, but also identify at each step from the W learning assurance how we can mitigate the risks of having the AI model rejected by the end of the execution of the complete pipeline and go toward the so let's say the implementation and the deployment of the AI model. So concerning the use cases, as I said, we rely during the whole experimental part of the project in two big classes of use cases. There is the toy use cases and the real use cases from aviation. The objective of the use of the toy use cases is, as I said, these use cases are less complex and accessible for everyone in the community, and that would like to reproduce the results and to verify what we are recommending in the project, for example, and also assess the most important thing, assess the applicability of the methods that we have selected in shorter data sets and more simple, let's say, tasks, before going to the aviation use cases that are more complex, from the higher dimensionality of data, more complicated tasks. There is other criteria that should be taken into account, such as the safety requirements, the system level requirements, etc. And then also the objective of these aviation use cases. We are in a research project for aviation, so it is normal that we go directly to the real use cases from aviation and have consistent recommendations as outcomes of the MLEAP project. So here is the big list of the open source and the toy use cases that have been used in the project. So the applications was focused on image processing, image classification, object detection, etc., but also the automatic speech recognition and a time series. So you will see why we have selected these different applications as for the toy use cases, because for the aviation use cases, we have also different applications where the AI can be a tool and a solution in order to help, for example, the air traffic control speech to text, which means we need to verify the spoken instructions by air traffic controllers and also for the crew, and to help understanding better and avoid errors. So here on this table, you can see a high-level viewed, in fact, ODD definition from the perspective of the projects. For this part, so there is data provided from the Airbus group, where the teams working on the two first use cases, ATC-STT and the third one, the AVI, they provided us with the real data collected from different airports, and French airport, and also the models that these teams have been already trained, and they started using and evaluating in these research internal project for Airbus. And the objective for us on the MLEAP project is to evaluate our findings in real use cases where there is already materials, there is already data, there is already models that have been developed, and we would like to evaluate the existing ones and how we can bring more solutions in order to enhance the existing ones, as we did for the open source data sets and models. So about the first aviation use case, speech to text for air traffic control. As I said, there is data provided from Airbus, but also for this use case, we used open source data. You can see on this table the list of open source data sets and the proprietary Airbus data set. So for this one, the data are not shareable, but we had made the same analysis using the open source data sets. You have the links to the data sets and also the models. There is the criteria, the different speech, the spoken English accents, etc., in order to evaluate the models and see the most important differences. So the objective for the MLEAP project on this use case is to evaluate the ability of the models to correctly translate the spoken instructions into text, regardless the accent, the background noise, the speed, etc. So you will see the results presented by my colleagues during this today's session. And for the second aviation use case, the automatic visual inspection. So for this one, the focus is to detect and classify damages on the skin of an aircraft, where the two important in the classes are the lightning strikes and dent impacts. Here you can see some example images from the open source with the mentioned references. And the challenge for MLEAP project here is to evaluate and to help the models reach the targeted performance of more than 95% accuracy in order to get the AI model accepted and industrialized and can be used by the Airbus teams working on this internal project. You will see also the results comparing the different models. And the last one, it is an open source aviation use case. So the EASA, as I think most of you already know this use case, it focuses on the reproduction, in fact, of the lookup tables using deep learning models, where the objective is such compressing the tables and have the models reproduce the same maneuvers in order to avoid the collision on different unmanned aircrafts where the ECAS system is already operating. As a final detail for this part, so the experimental work of the project have been supported by Airbus Protect, where we provided a dedicated server located in Toulouse, in Blagnac, on our site, with a secured access provided for both all EASA members, but also all the members from the consortium. Here are the characteristics. So it is a dedicated server to hold the internal data sets that are not shareable, but also the open source ones, and let the experimental work shared internally. There is also materials provided by Numalis, so the tool named Sample, which is used also for the project in order to evaluate the robustness of the models, and all the consortium members and EASA also had already access to this tool. So all data science related tools have been installed on this same server, accessible online. So thank you for your attention. This is all for this part. Thank you.
Thank you, Thierry, for this great presentation. So let's have this time only 10 minutes for question and answers. So as you can see on the screen, it is displayed the QR code for the Slido and as well as the password. So like we said at the beginning, please feel free to address questions directly in Slido. We already have a few, so just I will just let Xavier clarify one thing, and then we'll start with the presentation and the Q&A.
Yes, there were a couple of remarks of questions in the WebEx itself. So really, please use Slido. There was this interesting remark about data cost and complexity, and someone noticed that it does not need to be the case, but was indeed more a problem statement. And in certification, we often have interesting discussion about qualitative properties, and it often comes to the trade-off between additional cost and whether the industry has done its best effort. So that's where the complexity and cost argument could kick in. Obviously, if you have some application where data can be easily collected and does not cost much, that's even better. But it will probably not be the case in most of the complex applications we've seen so far. And maybe we can take the question one by one.
Okay, so the first question goes like this. So can you explain scale up to unseen data? This seems to misunderstand long tail event. You can statistically explorate to unknowns. So who wants to take this one? Cesare?
I think here what we mean by scale up to unseen data, it means here in the context the generalization and the generalizability of the model, the ability to have the same performance or acceptable performance on unseen data during the training, on the test data. And I don't know if maybe my colleagues would like to add something about the long tail events on the data. You want to add something? It's okay? Okay. I hope this answers the question.
Thank you, Cesare. Okay, so for the EASA, this one. So how can stakeholders know what competencies are required to implement AI application? So example, do you publish a competency guidance material for regulators?
That's not my part in the concept paper, but I will give the first answer and I will let François or Guillaume provide additional information. We have some objectives that are related to the organization in the concept paper, where we define how the organization should prepare for AI applications. And we have a set of objectives and means of compliance. Then the second part seems to be linked to guidance material for regulators. I'm not so sure what this refers to, but Guillaume, if you want to.
Yes, maybe I will just complement, but you said it well. We started thinking about the organization part. You saw yesterday in the rulemaking task, we have authorities requirements, organization requirements as part of the part AI. This is the place where we will clarify this. So today we don't have a guideline or a guide material. What we do it on a case by case, project by project. When we have a certification project, for instance, coming in, the DOAs actually are already scratching their heads on augmenting their competence scope and providing, let's say, a DOA update or slight change in order to include data scientists, this type of competence, I would say, to their organizational approval. So this is a case by case for now, and this is really coming through the part AI as a let's say confirmed, consolidated input in short. I would say mid of next year with the NPA, and then in 2 years or 2.5 years for the consolidated opinion. Thank you.
Thank you, Guillaume. So another question for you, Xavier. So how do you make the link between the WG 114 RMPs and MLEAP results?
Thank you for this very interesting question. That's actually the end of the presentation of the conference today. Indeed, this is a research project, and one of the key requirements from Horizon Europe is to make sure that the results are properly used. And so we anticipate to use the outcome of MLEAP to build our means of compliance, but we have some material that could be of interest to Working Group 114. I was engaged in 114. I will support a meeting with 114 in the coming weeks, and Guillaume, François, and the team are also engaging regularly with Working Group 114 to make sure that what we are doing in MLEAP is properly used, and is what we've learned in MLEAP is leading our involvement in this working group.
Thank you, Xavier. So, a question for you, Thierry. So, when are you migrating ECAS use case to a closer to realities certifiable avionics platforms? Will you still be able to run the same machine learning models, and what are the challenges?
Thank you for this big question, but unfortunately, I don't have a clear answer for this one, because on the MLEAP project, the implementation and the after implementation on the target system of AI models was not in the scope of the project. Maybe we will show later today some recommendation after the implementation what should be done, but it wasn't on the experimental part.
Maybe Thierry, I will just complement saying it's a tough question in the sense that it's ongoing work also on the other side. I'm really not into this project, so I cannot say much more details. But talking about it with our chief expert on avionics, it's an ongoing discussion how to indeed certify the ECAS X at large, and not only XU that you use. So this is really something we cannot give a concrete answer right now. It's absolutely important topic, ongoing, very relevant to the full community, because it touches upon really a number of products and ongoing work. Yeah.
If I can add something, MLEAP is dedicated to the machine learning models. When you are speaking about certification, it's at system level. So there is two different things, and for the certification, you need to think about the system and not only what we are doing for the software and so on.
Thank you. A question for you and for you, Arnaud, on Numalis side. So there is a tool mentioned from Numalis. The name of the tool is Sample, as I recall. So what does this tool do for the project, and how in general?
Right, so Sample is a solution we developed at Numalis. It's focusing on robustness assessment and also explainability. It uses only formal methods and mostly abstract interpretation in order to run. And so for the project, we use it extensively for the assessment of the LM12 requirement. I'll delve more into that in the presentation this afternoon on task 3. But yes, it was mostly used to assess robustness and explainability for the project using formal methods.
Thank you, Arnaud. So a question for you, Jean-Baptiste. So isn't the generalization guarantee an important part of machine learning models' robustness? Why are they two different tasks?
So for me, the generalization is looking at the average performance on the full ODD, when the robustness can be seen more as a standard deviation related to the average. And then they are complementary. Of course, there is some theoretical analysis where you can see that there is a strong relationship. We speak about generalization bounds this afternoon, and you will see that some generalization bounds are based on the robustness stability of the model. So for me, there are complementary properties, and they are key in terms of ensuring proper performance on a single input you can have. Not to look only on the average, because the average on the full ODD doesn't mean anything concerning the uncertainty quantification you can have when you are speaking at system level. Arnaud, if you want to add.
No, I think you clarify that. Also, it was part of the tender to have this task, like that, like they were. So we were following also the what the EASA asked for, but there is relationship between the two, and we tried within the integrated pipeline to show how all of these tasks answers each other's and work together.
A follow-up question for you, Arnaud. So what type of formal methods, technique does sample use? Can this tool provide counterexample that can be used back in the training process?
So, like I said, we use mostly abstract interpretation. So for those who not up to speed on that, so it's basically envelope computation. So you say I want to verify the behavior of a function on this part of the domain, and these compute an over approximation of these images of the function. It can tell you when a property is true, but it cannot tell you when it's wrong. So it tells you either yes or I don't know. So no, we cannot provide a counterexample. So it's not a complete and exact method. But that's the trade-off for scalability, because complete and exact methods usually are not able to scale to large models, large neural networks, for example. So that's basically the trade-off abstract interpretation is allowing to have.
Thank you, Arnaud. A question for you, Xavier. So ACAS X is a low dimension task that was solved from a verification perspective years ago. Did you consider tasks such as runway detection or object detection?
That's also a very important point that is raised here. We've looked at use cases that were not only high dimension, but also low dimension. So that's why we've kept ACAS-XU when we were proposed a series of use cases. What Tisri described is that we had three use cases. The first one is ACAS-XU. Then we have image recognition with a defect and maintenance case. And we have also a speech to text, which is also high dimension. So we wanted to keep ACAS-XU. It's a benchmark on one hand, and it's also helpful to assess theoretical bounds in terms of generalization, for instance. It's true that ACAS-XU is very well known, very well studied, but we thought it would also be useful to make the link with previous work.
Thank you, Xavier. So another question goes like this. So how do you deal with the lack of data for certain ODD scenarios?
So concerning the lack of data, so it is a bit anticipated question. You will see on this afternoon one of the tools that already used in MLEAP to deal with this challenge. Data augmentation, which is one of the methods, but is not the only one that can be used. And you will see an impact of this tool on the performances of the model, but also what brings to cover the ODD and what it can add.
Okay, so maybe a question for you, Guillaume or Francois. So how do you imagine for continuous safety assessment occurrence reports? So how airlines will make difference between crew, human factors, and AI in investigations?
Okay, yeah, I will answer this one. So continuous safety assessment, as François presented yesterday, is a complement to things that are already in place in terms of incident investigation support, usage monitoring. This is already in place. We add up a block to make, let's say, to bring the attention on the necessity for machine learning to have recording, specific recording capabilities and monitoring capabilities so that we can record the monitorings. So that's what we envisage. We have to delineate properly the boundaries of what we really want to mandate. That's clearly something we do with use cases. We will be really careful on that, but we wanted just from the start to say there is an additional effort on monitoring data recording that we will ask, and of course data analysis. After how regular, what is the pace, etc. It can be case by case today. We will see if there is a need to precise this information. This is the scope of what we have in mind, but again, it was to put a first element of importance in the concept paper and in anticipation of the rulemaking. I think there was a second part of the question. Just thinking, it was. Don't see it anymore. Yeah, I can't remember. Oh, yeah, exactly. That's the point I was looking for. Yeah, between the human and the AI, we have really an objective already on the ethical side to say a human should know whether the interaction is with an AI-based system or not. That's one first element. But definitely in the recording of output from the system, we shall, by all means, have a very clear distinction between what is a human input versus a system output or system input output. So this is really something we will clarify. Yes, absolutely. That's a key point.
Thank you, Guillaume. So let's take two more questions and then we'll have the coffee break. So the next question will be for you, Arnaud. So how former methods mentioned during the presentation fit for certification purpose, in particular for robustness demonstrations?
So I guess on this point, it's you have to see it as a whole because no method is perfectly fit. Combination will be necessary. So it's not only about you have to use only formal methods. No, you have to also consider statistical and empirical methods. And so what we're trying to show in the MLEAP report is the complementary aspect of each one that you can use in order to cover as much as space as possible of the input space and demonstrate robustness across it. Regarding formal methods, what is important to note is that it is one of the methods that allows to tackle high dimensionality input space. Because if you want to use statistical approach and sample across an n-dimensional space, you're probably going to spend a lot of time. Whereas if you want to have a local view of this n-dimensional space, you can have it using formal methods. So by combining both statistical to explore and formal to assess locally, you can map better the input space. But again, I'll try to show it to you in much more detail when the presentation of task 3 will come up this afternoon.
Okay, thank you. One more question. So for you, Thierry, so for Airbus use case models, I assume that training is done on the GPU server, but are the inferences designed to run in edge devices, except on laptops?
Thank you for this important question again. So I will say there is both. And there is differences between the models that have been selected. And this is one of the important criteria that you should take into account when you select the model to reach one of the objectives. I will say more this afternoon and by my colleagues later. Thank you.
Hello, everybody. So I'm Zen Ribeiro, task owner for task 1. So I'll be presenting our findings on the report. So first, to talk about task 1, we will set up some definition to be sure that we are on the same page. So task 1 was about data completeness and representativeness, and we consider that a data set is complete if it sufficiently covers the entire space of the ODD for the intended application. And we consider a data set as complete, as a representative, if the distribution of its key characteristics is similar to the actual input space of the intended application. So, as it was stated earlier, MLEAP was divided into 4 phases. During phase 1, in task 1, we identified the assessment method that we would be studying for the rest of the project. In the report, there are more than 80 methods that are discussed, and around 20 of them that are selected for further testing. Then during phase 2 and 3, we tested the method on toy datasets. So as explained earlier also, because some of these methods require complete re-implementation, and the result analysis with respect to data completeness and representativeness is not always straightforward. And then on phase 4, we capitalized on what we did on the previous phases to apply these methods on actual aviation use cases to provide some concrete information for the readers. So I know that this kind of talk can be long and tiresome for some people, so I'd like to cut to the chase and present you with some key takeaways right now. So the first point that I want to discuss is that we found that methodologies exist and data quality assessment is quite evolved, but it still lacks structure. In the report, there is extensive discussion about the influence factor that surround data completeness and representativeness, and none of the methods that we found allowed us to study these properties with the influence factor isolated, which would be the most rigorous way to operate. There is also the question of completeness being harder than representativeness, because as you will see, a lot of the methods that we found are compatible with the assessment of representativeness, but less of them are compatible with the assessment of completeness. There is also a question of the combination of AI task and dataset that usually requires some tailored assessment method. So that's not to say that there is not some genericity in the data assessment process, but there is also an extensive need for customization that must be taken into account when working on these questions. One of the findings of the report is that there are two real pillars for data assessment. It's the ODD on one side and the model on the other side. So the ODD is an upstream specification document that will allow you to specify the expectation that you have toward your dataset and to build your dataset according to these expectations. But then this data will be fed to your model, and the model will exhibit some learning processes and learning behaviors that will put some of the choices that have been made before into question. And the model in this case can be used as a feedback source to maybe make the dataset evolve and better fit the model learning behavior. And finally, there is a notion of trade-off between completeness and representativeness that must always be kept in mind. The idea being that if you want to enforce perfect representativeness in your dataset, you will have some rare cases that will be underrepresented, and when you feed them to the model will not capture them correctly. So to ensure performance on these samples, you will have to increase the number of samples that are that cover these cases. And in this case, you will be training off some of your representativeness for the sake of performance and completeness in the end. So it's always a trade-off that must be kept in mind. So MLEAP was about experimentation, and I will be presenting a quick tour of each method that we explored. Here they are summed up, with the light blue ones being the ones where we could apply the method on the aviation use case. So the first method is the PCA, so Principal Component Analysis. It's a classical dimension reduction technique for quantitative variables. We applied it on AK6U and AVI. The intuition for data completeness and representativeness in this case is that a complete and representative data set would yield a homogeneous scatter plot. So for AK6U, the interest was that it is supposed to be a complete data set. So what would happen if we visualize such a data set? And also for AVI, the motivation was data augmentation and to measure the impact of data augmentation on completeness and representativeness. So regarding results of PCA on AK6U, we can see here some bidimensional projection of the points in the principal component axis. And we can see some interesting phenomena. We can see some regular patterns of straight lines of data points that appear with more density on the sharpest maneuvers. So here there is left turns as opposed to a weak left. We can also see the gradient of action with the sharpest maneuvers on the left of the plot and the softest maneuvers and the clear of conflict on the right. PCA also allows to see the quantity of information that is embedded into each of the axes. So this is the goal of the upper histogram, where you see the quantity of explained variance for each principal component. Here we can see that the first axis embeds all the variance, which suggests that the dataset is quite repetitive in terms of feature pattern combination. And on the lower histogram, you can see the distribution of samples across classes for a given input classes. Here the given input class is clear of conflict, and you can see clear domination of the clear of conflict output class, and a really low representation of the other classes, which is so this high imbalance can be a result of a strong representativeness enforcement. But the question is such a data set correctly learnable? That's a real question. I don't have the answer. Moving on to the application of PCA for the AVI dataset. There is so here on the left you have the PCA for the base dataset, and on the right on the augmented dataset. And what we can see is that we have on the augmented dataset a higher density of points, which is good. It suggests an increase in completeness that is quite positive. We can also see that the dentalB class, so basically the red dots on the projections, do not augment in number, and maybe even looks like they are less represented on the augmented dataset. So this is a point of vigilance. And we can also see that the scatter plot is shifted on the left, which results in a smaller spatial coverage, which is not that positive. It suggests a decreased representativeness of the dataset. So here there is maybe a mitigated effect of the augmentation for this dataset. So the next method is the graph-based analysis. So this is preferably usable for low-dimensional qualitative variables because it has a strong combinatorial complexity, because it's an exhaustive coverage exploration of the combination of features. I will talk about it on a toy dataset, even though we have some discussion on aviation use cases, but the results are more interesting if I stick to the toy dataset use case. So the general idea of this graph-based analysis is if you have a dataset where each sample is a combination of feature, you can draw the graph of all feature combinations, with some feature being static and some other features being variable. So here you can see that if we consider an individual through its sex, whether or not it has a Netflix account and whether or not it wears glasses, you can draw the graph of all combination with, at the top of the graph, all features being variables, so any form of individual, and then making some features static in an increasing manner, with the bottom of the graph being the actual sample in your dataset with all features static. And the idea here is to set a threshold value and count each combination of a feature to see where at which combination you do not meet the threshold, and when you don't meet the threshold, you have what is called a maximum uncovered pattern. So in this case, we see that the combination 100 is underrepresented, and that actually the combination 1x0 is also underrepresented, and since 100 is dependent on 1x0, our MUP, our maximum uncovered pattern, would be 1x0, and we know that to increase correctly the coverage of our dataset, we need to increase the coverage of the 1x0 combination rather than just the 100. So this method is inherently useful for completeness, since completeness and coverage are confounded here. It can be tweaked for representativeness. For example, if you use a clever threshold value, or if you define several different thresholds depending on the combination that you study in accordance with your ODD. Of course, there is this limitation that if you can't cleverly choose a threshold, it's a limited method, but that's generally not too limiting. Next method is entropy analysis. So this one is for high-dimensional data, especially image and audio. It was tested on the AVI dataset, and the intuition here was that a heterogeneous entropy distribution across classes would be indicative of a representativeness discrepancy. So again, since we are working on AVI, we are comparing the base dataset versus the augmented dataset. So this is the image-wise entropy distribution of the samples across classes. And what we can see is that on the augmented dataset, we have broader boxes with similar means, which suggests an homogeneous extension of the dataset, so a positive effect of the data augmentation. But in the same time, we can see that we have larger whiskers and more outliers, which is quite problematic because it suggests that there is a lot of heterogeneity that has been introduced, and this is not desirable in this case. We can also compute just label-wise entropy to get a single score. And we can see here that for the DentLB class, we have a negligible increase, so probably the data augmentation didn't have much effect on this class. There is a reasonable increase for the DentAL class, which suggests that maybe some performance gain is to be expected for this class. And then for the last class, there is a very important increase that is probably beyond what should be expected from data augmentation, and so probably a point of vigilance when measuring the performance on this class. So entropy analysis is a coarse-grained tool that represents a good entry point, but is very dependent on the data set that you have to begin with, because if you have a lot of diversity, for example, in the images across classes, you will see discrepancy in entropy, but they do not relate to properties such as completeness or representativeness. The idea is that you should have a homogeneous kind of images, for example, to exploit entropy as an insight for completeness and representativeness. So the next method was a sample-wise similarity. So it's also a method for high-dimensional data, and its interest rests in the fact that it could be useful for data that can be harder to assess, such as audio. This method uses embeddings as proxy for the assessment. The intuition here is that the embedding space encodes latent properties, and that using similarity metrics on the embeddings would allow to measure the link between these latent properties. So just to be clear, what is an embedding? So I'm going to stick to a simple definition. I think most of the AI systems that we will be dealing with in the future will be neural networks. So I will give a definition of embeddings for neural networks. Basically, an embedding is an input representation into a vector space that is made by the model. It's generally lower dimensional than the input, even though it can be quite high dimensional, but just lower than the input. And the idea is that embeddings, by performing dimension reduction, encode a lot of latent properties on the content. And the idea is that if you can, if you know what are the properties that are encoded, you can exploit them. So the objective here was to assess the completeness of an audio dataset relative to the content of what is spoken on the audio signal, which is not doable directly on the signal. And for that, we needed embeddings that encoded some semantics. We tested 4 types of speech embeddings, and none of them had this semantic aspect, so we had to cut short the experimentation. But I still wanted to mention this method because I think it's really important for future applications, because it's virtually compatible with any unstructured data, and it brings the structure that is lacking to this raw data. Of course, the big limiting factor is that it depends on the properties that are encoded into the embedding. And if you're using pre-trained embedding, you don't have any control over the properties that are encoded. It also requires a relevant similarity matrix, whose choice is not completely trivial, but it's not the main limiting factor here. So then we didn't have to only re-implement methods. We also had to test some tools that already existed. For this, we tested CleanLab. We chose CleanLab because it was a prominent open source software suite. It claims to be able to process images, audio, text, and tabular data, which is nice. And it provides metrics about mislabelings, outliers, and near duplicates. And also some metrics that are specific to some data type, for example, odd ratio for images. And we tested it on AVI. So the main limitation that we found with CleanLab is that you have to get insight over what is about outliers and labeling errors. You have to use a model. You have to provide a trained model to CleanLab. So for our preliminary experiments, we were able to provide this kind of classifier, and we actually performed a contrastive study using a very accurate classifier and a less accurate classifier. And you can see in the green box what CleanLab estimates to be outliers for the best performing classifier, and in the orange box in the worst performing classifier. And you can see how in the green box, the input, the samples do look like outliers. The problem being that moving to AVI, we could not provide a model because AVI was an object detection task, whereas NIST was a classification task, and that's the main limitation of CleanLab. It works only on classification models. So for AVI, we were stuck with general information about the number of blurry images, the number of odd aspect ratio images, etc., which was less insightful. So obviously, CleanLab is not a universal solution. However, it's a very useful suite for classification models. In this case, it will help highlight edge cases, corner cases, and hard cases. But it will work only for classification tasks. The assessment heavily depends on the model, so you need to provide it with the most mature model possible. And the idea becomes, is it worth it to backtrack on the data when you already have a mature model? It's not a single yes or no question. So sometimes it's relevant, sometimes it's not. And in the end, CleanLab does not completely automate data assessment. It's just reducing the cost by highlighting some area of focus for human examinators. So then we are moving to model-centric approaches with neuron coverage. So the idea of neuron coverage is to observe the activation states of a neural network. The interesting thing with model-centric approaches is that they are data agnostic. So the intuition here was to observe how the model would react to data and how it can relate to lacks of completeness or representativeness in the data. We performed our experiments on AVI, and one of the nice things that we found with neuron coverage is that you can compute it at several different levels of granularity. So the blue curves on the left will show you a single aggregated score of coverage for the entire model. Then you can break it down layer-wise. That's the right graph, and you can see how some layers behave differently from others. And then you can compare the base dataset with the augmented dataset. And the observation that we made is that it shows no difference in trend. So probably the model is not leveraging the augmented data. So this neuron coverage method rests on the selection of an activation threshold over which we consider the neuron as activated. You can go deeper in terms of visualization. Here you can see activation maps that are basically neuron-wise. And we perform these activation maps for different threshold activation to see how the threshold can be selected. And you can see that the lower the threshold, the most activity you can see across the network, because actually the deeper you go into the network, the most activation you get. So this is particularly visible on the first activation map with threshold 0.1. And we selected the 0.65 activation threshold as our reference, because even though it inactivates a lot of the layers, in the last layer we can really see some activation patterns that were really nice and diverse, and probably the most interesting for a contrastive study between the base and the augmented dataset, which is presented here. But once again, you can see that these activation maps show that there is no augmentation and no change in the activation patterns between both models, which suggests that again the model does not learn from the augmented data. So neuron coverage remains an interesting method, because it's very flexible in terms of the visualization that you can do. You can choose your level of granularity. You can choose whether you do curves or other kind of visualization, so you can get something very precise or something very aggregated. It also enables monitoring, which is interesting, and you can really see at every sample or every batch how the model behaves. The limiting factor is that it requires white box access, which is trivial for in-house model, but it's limiting if you're fine-tuning models that you found on open source. And it takes some engineering to plug all the probes where they have to go, but that's not a real limiting factor. It's just something that has to be budgeted. Then another model-centric approach is feature space characterization. This one revolves around 4 metrics. And the intuition here is that observing the feature space and finding a homogeneous feature space is indicative of a complete data set, at least learning-wise for the model. This method was also tested on AVI. So the first metric is called equivalence partitioning. It measures the class-wise balance of a data set. With all classes that should reach an equivalence partitioning score of 1. So on our preliminary experiments, we worked on the NIS dataset, which is a very well-balanced dataset. So you can see how all scores converge toward the score of 1. And when you apply on AVI, you can see that there is a strong discrepancy over the data, which is normal, since AVI is a real life data with some impossibility to gather some kind of data, but it shows how the discrepancies are distributed across classes. So then the second metric is called the centroid positioning, and the idea here is to provide a score that indicates the homogeneity of the samples in a given radius. And the idea is that the larger the radius, the lower the score, the better overall. The problem is that we didn't know how to make sense of this specific metric, because as you can see on the NIST and AVI dataset, both scores diverged almost immediately. So we could not really leverage this metric to provide some insight on the dataset, but it's still part of the method, so I'm presenting it. Then the third metric is called boundary conditioning. The idea here is to compare the confidence score that are produced by the models for its best and second best guess, and to use this score to define the decision boundary of the model as a range in the confidence score. So for our NIST preliminary experiment, you can see in orange the distribution of the confidence scores for the prediction, the best guess of the model, and in blue the distribution for the second best guess of the model. And you can see how they overlap at some point, which is our decision boundary. And then working in this range, we proposed a visualization that is inspired by what CleanLab proposes. With at the center of the samples, a sample that comes from the range, so a sample that is on the decision boundary between two classes. And so the idea is that on the left you see a high confidence sample of the best guess of the model, and on the right you see an example of the second best guess of the model. So that was nice. And then when we tried to apply it on the AVI dataset, we found this distribution, which is not a neat binomial distribution that we can exploit. So basically, we could not identify any range, and that's probably due to the fact that AVI is a detection task, whereas NIST is a classification task. So so classification tasks probably tend to define more clear decision boundaries, whereas in detection task it's more complicated. So then the last metric is called pairwise boundary conditioning. So the idea was to aggregate all boundary for each classes. So we propose to visualize it as a heat map. And the idea is that you can see the most confused classes for a given prediction. So if the model predicts 1, you can see that the hottest the hottest class, so the class where it most often hesitates, is 6, and you can see that for other classes. And the idea is that since we could not find any boundary, any decision boundary for AVI, we could not exploit this specific metric. So this method is data agnostic, but it's not task agnostic. So something to bear in mind when using this method, and when using other method, possibly there is always a limiting factor that comes in your hand. So then there is the completeness ratio method. So basically these are only metrics for tabular data, which can be used for the metadata of more complex data sets, which is always useful. It illustrates different notion of completeness, with completeness being defined as the absence of missing value in the features. It was not tested on aviation use cases, and I'm just going to brush over them quite quickly. So the idea was that in the literature we found 4 metrics that are called documentation, breadth, density, and predictive, and we applied them on a toy dataset, and we derived 3 other metrics that we call G1, G2, and G3, respectively the column-wise, row-wise feature completeness and the absolute ratio of missing value. And the final method that we tested was a risk-based approach proposed by the BSA, the Business Software Alliance. It's initially aimed at addressing population bias in demographic data. So the motivation for investigating this method was that bias is a facet of representativeness. And the question that we asked is this method, is it possible to extend this method to any type of data, or is it really stuck on population bias on the demographic data? The answer is that this method can indeed be considered data agnostic. And another upside is that it's easy to apply because it requires a few tools, but it requires a lot of expert knowledge because it's mainly guidelines and not a straightforward, very hard method. So if you don't use expert to apply it, you might not find conclusions that are insightful enough to really work on your data set. So to conclude, it is important to understand that MLEAP was a research work. It's not a prescriptive work. Data qualification is a hard thing to do. And the idea for MLEAP here in task 1, at least, it was to showcase the methods more than a prescriptive method to apply. We still consider that applicants are a driving force that can bring new methods to the table. And the only limit being that this method must be insightful enough to help applicant remain accountable on their proposition. There is also the fact that the aeronautic sector is at the tip of the spear for AI reliability, and so applicants will probably be pioneering the development of industrial-grade methods for AI reliability. So, thank you.
Thank you, Sven, for the presentation. So now let's continue with the Q&A session. So we'll have 20 minutes. Just before we get started, just coming back on the question that were previously addressed that could not be answered during the last presentation, we will try to answer them throughout the day. And just one more information. So this event is recorded. I don't know if I said that already. And so the presentation as well as the recording will be shortly shared after the event with you. So we'll be available on the EASA MLEAP project page and as well as on the Airbus Protect MLEAP page. So let's get started with the questions. Okay, so first question goes like this. So about task 1, can we expect a dedicated data qualification guidance materials for machine learning similar to existing tool qualification guidance for development assurance?
Désolé, je lis derrière toi parce que...
Ah, it's on the screen over there.
It's not on this one. Yeah, now it is. Now it is. There is some answers to this question in chapter 7 of the report. I think it will be discussed later in the day. So probably this question will find some development during this phase.
I mean, what we are seeing in MLEAP is that there are some outcomes that can be useful at various levels. The tool qualification guidance is a standard, is a different type of, standard that goes along with DO 178 and that was integrated. I'm speaking under Guillaume control in the latest version of the DO 178C. Whether we anticipate the possibility with MLEAP to create new standard maybe is something we will need to discuss with working group 114. We have one standard in development at the moment, but certainly the methods and tools that we have addressed in this research project could find their way in some air standard or the type of standard. Now, have we identified the need for data qualification guidance material? That's not something really that we have identified as such, but as Sven mentioned, we have a set of recommendations and good practice. So maybe we will need to do we need to find a way of using and publishing in a more or standardized way with a set of recommendations. And we will see how we do that in the future.
Thank you, Xavier. So one more question. So this trade-off between completeness and representativeness means that following the operational distribution is not a must for the training model, isn't it?
Yes, it's really a choice that has to be made during the development phase, with the idea that representativeness is important to some extent, and how should it's also a question of what are your edge and corner cases, how rare are they, how homogeneous do you want your learning to be, your performance to be? So yeah, it's not a must. Representativeness is not a must in my opinion, but it's really a case-by-case question for me.
So the model-based approach, sorry, did you put it up? Okay. I cannot find the questions anymore. Okay, sorry. So the model-based approach being data agnostic raised the question how this is data completeness, or doesn't it contribute to a different property?
It might be considered another property, but the idea is that when you are using a model-centric approach, you get feedback from how the model learns your data. So that's a definition of completeness that is model-wise rather than absolute from the ODD. So as I mentioned in the beginning of the talk, the ODD and the model are both pillars that has to be leveraged to build the dataset. Obviously, when you get some feedback on how your model processes your data, there is a part of the problem that is the model. But as you converge toward a mature model, the question of modifying the data rather than the model becomes more and more interesting. So that's the idea of the model-centric approach.
So one more question. So from the result that you presented on AVI project, the data argumentation seem not improve metrics. Have you an idea on why?
No, we don't. We don't have an idea. We could not go into a deep study of the effect of data augmentation. Off the top of my head, it could come from maybe an augmentation procedure that is not in line with the problems that the model has in terms of what it needs to learn, where are the weak points in the model. But no, I don't have a definite answer on this one.
Okay, so regarding the demographic method, could you detail the expertise needed in aerospace? We are supposed to have experts.
Yeah, but the idea is that the method was developed by demographic experts, and so if you want to apply its principles to your use case, you should have experts about your use case, your data, but that is just it's just that.
A follow-up question from Gary. So, is it not data fit for purpose rather than qualification? The objectives are to target confidence in the data content aligned to the ODD and rare cases.
That's a good point. When the question was raised by Antonio on whether we want to have some standard to deal with qualification of the data, that was one of the reasons why I was a bit hesitant. I think, as you mentioned, the question today is whether the data is fit for purpose. Whether we want to go further than that, I would say it's an additional step, and this is not really what we are looking at the moment. But whether a dedicated standard or R could be done in the future on data and how to demonstrate it fit for purpose is an open question at this stage, I would say.
Okay, thanks. For me, going towards qualification would be unnecessary. I think it's the wrong move. We just need to assure, as an applicant and for the approver, that the data that we're using is fit for purpose. That's part of the regulation, fit for purpose, inside qualification, and that we've considered the ODD and the rare cases in the testing and examination for robustness, etc., and stability. Thanks.
Yes, in fact, for the concept of qualification on the project, what we consider as actions for data qualification is to focus both in the vision, if it is representative and complete, to represent the part of the ODD that we are addressing. In order for the evaluation part of the AI model itself, we can say that according to the scope of the ODD and the data that we have verified, it is in the defined scope of the ODD, our model is good. It can generalize, it is robust, etc. And of course, the rare cases have been subject on our analysis. So on the task led by Numelis, you will see further experimental analysis on the edge cases and the outliers.
Okay, so for task 1, do you think it would be possible to classify aviation use case on AI tasks to generic tasks and maybe map them to AI levels?
Aviation use case, maybe it's a bit ambitious because there will be a lot of use cases. But for AI tasks, the combination of AI tasks and use cases, yes, I think that will be a question of how do you position the task in terms of AI level. We didn't think about that in the MLEAP project. That was not the scope, but I think it's an interesting way of seeing things.
Maybe if I may, Guillaume speaking, this link is always difficult in the sense that from all the use cases we've seen so far, the link to AI levels is really a case-by-case assessment. Yeah. So I see exactly what you say, Sven. Let's see what we can genericize as maximum, but it's really so based on the concept of operation, the ConOps, that at the end of the day, generally classifying, even if you say, I don't know, there was a question yesterday, use space, is it necessarily level 3B? Possibly because the ConOps will bring us there, but it depends really on the system, on its usage, etc. So difficult probably to be generic on that, but yeah, interesting to think about it.
It's an interesting point of view.
So this question is not for you. This question was, it will be for Xavier. It was addressed earlier today. So are there any issue to be concerned about regarding data licensing of the example used within MLEAP?
We've used what we've called toy use cases that were in the public domain. So data licensing is not a concern for this use cases, but we also wanted to look at complex aviation use cases from the industry. And obviously for the AVI and some of the STT data set, some of the data is owned by the industry. So we have access to it, but we won't be able to share the data or the model in the future. I believe we have clearly identified the data set, the models, so you can also contact the Airbus or Airbus Protect if you want to cooperate with them, but it's beyond this R&D project.
So I have the feeling that data augmentation is understood as data synthesis. Augmentation just makes the model insensitive to some transformations.
I agree with this. I partly agree with this definition, and I don't think we mistake data augmentation for data synthesis. Maybe Airbus performed the data augmentation, so maybe they will be able to provide some more insight on what has been performed on as part of the augmentation procedure. But for me, it was not data synthesis. It was really a goal of augmentation.
Yeah, exactly. It was related to the ODD definition to take some transformation that can help us to increase the coverage of the ODD. But there is no virtual data generation and so on in our case.
So have you used data augmentation both for the training and validation data set? Isn't it validation with augmented data quick?
Again, more for Airbus.
So yes, it was used for the train and validation, but we kept the test data set with real data without any augmentation, just to have a reference and to secure that what we are optimizing is really fitting our expectation in terms of real world activity.
So are the methods are the methods to rate completeness capable to detect a missing physical connection? Example for AVI training dataset represents all color except red.
The methods are not able to detect this kind of maybe on a classification task, probably CleanLab would be able to detect this kind of problem, but the model-centric approach might exhibit some strange abnormal activation pattern, but I don't know. I don't know for the other methods. It's kind of it's an outlier detection case. It can show up, but it will not. It will require human intervention to see how this outlier, why this outlier is an outlier.
Can I have a comment, a suggestion? Yes. Can we look at the question? Can we look at the question with more votes instead of look at the most recent questions?
Just for clarification, since here it was more in the scope of task 1, that's why we are filtering first to answer all the questions related to, with task 1, then address the other ones now and during the day also. So don't worry, your questions will get answers.
I don't have any questions. I just followed yesterday and then answering the popular question.
Okay, so do we need to assess the data quality for training models? Shouldn't we apply the MOC to the generated product and verification mean?
You want to take this one? Can take that one. The approach that is developed in the EASA concept paper is integral. So our view is that we should not only focus on the generated product and the verification step, but like what we do in development assurance, at all steps of the development of the AI application, the EASA view is that we should pay some attention to some key aspects that we have identified through the concept paper, and data quality is one of them. Just verifying the final result in our view may not be sufficient, but that's really at the core of the EASA concept paper. That's a good question, but our answer is more, we really believe that from day one, from the very beginning of the W, there are some compliance demonstrations to be performed.
So did you work on metrics to check the data use for the training are representative of the operational design domain?
No, because we didn't have any ODD, and that's a problem that we see. Probably it won't be a problem for aviation applicants, but specifying the ODD is really not in the good practice of AI in general. I'm not targeting anyone, but it's not the most obvious move. And that's why we really stress the importance of the ODD as an upstream source of information for designing the data set.
Thank you, Sven. So maybe let's come back on the question that were previously not addressed but not answered. Okay, so this one. So the objective was to identify the MOCs based on EASA machine learning guidance. Do these cases analyze how these machine learning MOCs work with the existing MOCs that they must support? Who wants to take this one?
Yeah, I would take this one from a global perspective, Guillaume speaking. we really strived in the concept paper from the start to embed ourselves in the notion and the whole picture of what is development assurance today. So if I take really the airworthiness product certification thinking, we verified, and it was not a given, we verified that we can embed the framework of learning assurance together with, and you saw the V and W connected together, and that's exactly the purpose, working under the notion of certification specification requirements 1301, 1309, or 2510 if we look at other framework. So we wanted really to embed the learning assurance as much as possible in the global picture of development assurance, which we managed to do. And again, it was not a given because 4 years ago we got questions saying, are you really sure that you can put a W and the learning assurance at this level? AI is much wider. And actually, we answered that by saying, yes, AI is much wider. That's why we have level 1, 2, 3. But in terms of development assurance, let's call it design assurance if you want to make it large, but I prefer the term development assurance. We embed everything in the same context. So to answer the question, yes, also in the MLEAP, the idea was to embed those MOCs specifically for specific objective of the machine learning assurance in the big picture of the connection with implementation, for instance, and the use of classical standards, as we were discussing yesterday, for software, hardware implementation. All of this is really working together. So we didn't find initially, but also with MLEAP, any contradiction on the capability to live with existing standards. Yet I would really reinforce the message given yesterday by WG114, G34. The working group is really also connecting to us with the notion of having a layer that we call the constituent, the MLC, the machine learning constituent, being really a novel layer between system and item. So we don't say there is no novelty, but it's totally embedded and it fits super well with system development assurance and item development assurance standards, principles, methods, and AMCs, if I'm thinking to the big picture on EASA side. So I think that answers probably the question. Thanks.
Yes, thank you again for the answer. Just to add some data, so if you have not yet checked the whole document of the public report, so you will find at the beginning of the report an alignment between the different terminology used on the EASA documents and the literature, but also the existing documents of the standards, just to verify first the alignment between the concepts, what needs to be verified, the targeted concepts by the means of compliance, and how we can drive also the roadmap of the project in order to verify all of them.
Thank you, Thierry. So did you analyze each task with specific use case, or do you have a use case you have analyzed, or data properties, generation, and robustness together?
And here again, so you will see on the presentations by my colleagues for task 2 and task 3 that these use cases that have been already presented as the results in task 1 have been also used for task 2 and task 3 in order to verify the generalization, the robustness of the models. And at the last part on this afternoon, you will see how the cross analysis between the different tasks can serve both the generalization, the robustness, but also can benefit from the outcomes from the data.
So the open source data set do not always represent what we have with real aircrafts. Do you collaborate with any real project happening in the industry?
Yes, for sure. I think this question had been asked before seeing the use cases. As you have seen, so we used the open source data sets, but also there is the industrial data sets and use cases that comes from internal projects by Airbus, and all the experimental results have been verified by EASA.
So, what is missing from open source or commercial tool for data handling and analysis with respect to the specific needs in the aviation domain?
I'm not sure to do the lesson of commercial tooling. I'm honestly, I'm not an aviation expert. I would not be able to discuss lacks that I have seen relative to the aviation domain. Now, as I said in my talk, in general, the core of the discussion in task 1 is that for the properties of completeness and representativeness in the data, there is a lot of influence factor that comes into play, and there is no method, commercial or not commercial, or anything you can implement that will address these influence factors in isolation, which would be the most rigorous way to proceed. So, to me, that's the main limitation. But that's not even specific to aviation. That's for any domain. I think it's critical for aviation, but it's not much more than that.
Maybe if I can complement on that, I think what might be missing specific to the aviation domain is the notion of the ODD, which is really tied to the aviation industry, but is not at all known from the tool makers in the AI domain, which are not considering at all this concept. Or maybe they're considering something that might look like it, but is not as well defined and structured as the ODD you have.
Was there a specific process to select the set of relevant objectives for each of the 3 tasks considered? You want to take this one, Xavier?
Yeah, I believe T3 went into this direction already, but what you can see in the report in section 1.5 is that we have a chapter where the consortium explains their understanding of the EASA concept paper and on which of the relevant objectives, they have considered. And it is detailed, and then it's follow up throughout the report. Typically in section 6 for robustness, you will see for the experiment how LM 11, 12, and 13 have been assessed for each of the experiment. So it's
so have you analyzed any correlation dependence in between cross-task properties such as representativeness, generalization, completeness, robustness, generalization, robustness? This one's for you.
Yes, I can. Yeah. Yes, for sure. I think it is similar to the analysis cross tasks in the different use cases. For sure, there is too many correlation and dependencies between the generalization, the data representativeness and completeness, but also with the robustness. And again, you will see the whole detail this afternoon on the part dedicated to the cross analysis between tasks.
maybe task 1. Yeah.
So for training data representativeness, the final word should go through the model performance. This is what should drive the data representativeness.
I'm not sure that the question, it looks like an affirmation, but I agree with this affirmation.
I'm not sure if you've already responded to that one.
The idea that we didn't have any ODD, and ODD is not a current practice, a common practice.
Take them from the top.
Okay.
First one, it's easy.
Yeah, this is
for years.
Okay, so coming back on the question from the previous presentation. So does IK6U follow or is aligned with international standards? So, for example, the GRIS, SOAR, or others?
AK6U is a public use cases, and it's there is a dedicated international standard. It's DOED. I don't know the number from top of my head, but we shared with the consortium the exact references for this for the DOED. Then now, when it's come to JAWS, SORA, or other methodology used in the certification process, that's something completely different. But there is a set of detailed technical standard attached to AK6U. I can check and give the exact reference later on today.
So have you have any result if there are generalization issue with the concept of using toy use cases and aviation use cases?
It depends of what you have in mind. If you have a model, you apply it on a toy use case, you take the same model, applying it on a aviation use case. What you can do is assessing the capacity of your not trained model, or your before training model, let's say. But that's all. After the generalization capacity will depend on the optimization you are doing. The data set, are they representative or not? And remember that the generalization is a measure. You measure against what? Against the representativity and the completeness of your data set. So the measure you have at the end has to be balanced versus what you have used to train and to test your model.
If I may, in between, I was browsing. It's the DO386, the MOPS for the AK6U. Yeah, that's the one you were mentioning, Xavier. Thanks.
My computer.
Okay, maybe let's take one more question, and then we'll have the break for lunch. So this one is from Gary. So can you clarify the relationship or not with LM09 and EMP06 for model performance confidence?
So LM09 is requesting to perform an assessment of the performance of the trained model. EMP06 has to do with verifying the performance on the implemented model. So in a way, obviously, there is a relationship since we want to check that once the model is implemented, the performance are still holding. But I guess your point is going further than that. Maybe you want to clarify?
Yeah, my point is actually definitely going further, because obviously when I look at the EASA concept paper 02, it seems that against a minor effect, LM09 has an importance, but the minor effect for the IMP06 does not. There's an inconsistency, and I believe it's a mistake, because I believe that the IMP06 is more important, because you need to know when you've translated and you're putting it on an aircraft that you haven't degraded and that you've maintained the level of performance or accepted a reduction. But you have to measure that. That actually, the IMP06 is really important for me. So there's an inconsistency that I've spotted. And I just think that concept paper 03, you could look to this to see whether you can align for consistency.
Yes, Gary, Guillaume speaking. So definitely, we are working on. We are happy to get inconsistency feedback from all of you, and we will work on it in the issue 3 of the concept paper. We confirm the intent is here to rely on the performance measurement at implementation, so at inference model level. We share your view, so we'll check if there is an inconsistency or something missing in the proportionality table. Thanks.
Okay, thanks for that. And I would love to give some steerage towards your 03 concept paper, because, to try and help it move in a positive way, because I've spotted some sort of inconsistencies or whatever. So if you're open-minded, then I'm keen to support.
We are open-minded, very really welcoming all the feedback. That's really what we say always. And the concept paper is a moving document. It's not it's a living document. It's not something that we have graved in stone forever. And some of the inconsistencies we addressed at the working group last month, let's say, or just before we entered here. And we are working on others. One of them being, maybe a disclaimer for everyone, we are thinking about creating even an errata for this. One in the safety assessment, which you may think about, is it's a mistake in the numbering of an objective, which was at a certain number, evolved in the issue 2, but was not updated there. Meaning that there is an errata somewhere that might also trigger considerations. So anyway, the big picture is we gather the feedback and we will improve at issue 3 of the concept paper, definitely. Thanks.
Yeah, there was this question yesterday. I think, I don't know if it was you asking if we will improve safety assessment objective or non-safety assessment objective in issue 3. What was presented is what we want to add, but obviously the feedback we receive through different forums will be taken into account. And I think there was also a question about application with minor failure involved in minor failure condition, whether some improvement will be made for some objective. As Guillaume just said, it's the intent as well to take profit from issue 3. So.
Yeah, I think, as said yesterday, the claim is proportionality. And I think at 03, you need to look closer at the proportionality, because even in the ongoing standard, we need to look at ourselves for proportionality. We don't want to overkill a minor, even though it's novel. At the end of the day, we have to realize that if the effect is validated as minor, then what is the value? We always have to question the objective for value and not just apply it on industry for the sake of it. That's my point, is we really need to scrutinize it as we move closer to the end game.
One additional feedback. Hopefully, when issue 3, when we publish issue 3, the standard will be available. And as you know, in safety assessment, typically we rely on standard. So if the standard is covering the need, that will be very helpful for safety assessment.
So, hope you had a good lunch. I'm Jean-Baptiste Rouffet. I'm part of Airbus Protect. I was previously working for Airbus Aircraft, mostly in manufacturing engineering and digital topics. And today I'm a data scientist specialized in AI within Airbus Protect. I will present the task 2 content. We were working on this topic with Thierry, the technical advisor. And the task 2 was dedicated, as mentioned this morning, on the generalization property of the AI model. Our objective in this task was to identify and develop efficient method and tools for the quantification of generalization assurance level. To do that, our objective was to test available method and tools we have to evaluate the generalization bounds, to identify the barrier we could find in guaranteeing the generalization for given model. And we have also active work on identifying the means we can have in the learning process management to promote the generalization. This task is focusing on the 3 main concept paper objectives, which has been a bit discussed this morning, but I will reintroduce them. The first one is LM04, where the applicant should provide quantifiable generalization guarantee. The LM09 dealing with the performance evaluation of the trained model based on the test dataset. And the LM14, where we need to verify the generalization bounds we have with the test dataset. Our main focus has been the generalization bounds theory, how to use this theory to provide guarantee or to drive a bit some choice we can do in the learning process management. And second main focus was on identifying the driver that can influence the generalization. that to provide a kind of guidance for the developers to know where they need to act to promote generalization. In terms of steps, where we are focusing in the learning process, in the learning assurance process, we are focusing on the learning process management, the model training, and the learning process validation. So we are in the V of the W, which is dedicated to the design, and we are less working on the other V dedicated to the implementation. In terms of work done, so we had an approach in 4 phases. So the first phase was dedicated to the state of the art, where we have selected first 17 generalization bounds, and after deep analysis, depending on the use case that was available, only 13 remain in our portfolio. And we identify, thanks to the state of the art, the methods we have in the literature to boost the generalization, highlighting the limitation we can have associated to all those methods. The phase 2 and 3 was dedicated to the first test of the methods we have identified, and also a kind of approach for the calibration of the measure we will put in place on the aviation use case. So during those 2 phases, we have developed the code to assess and to calculate the generalization bounds. And here, as you can see, we have filtered some because it was very unrealistic to say that we can apply them in real use case. We trained different models and analyzed the performance with regard to generalization, and we have identified the issue and propose improvement. The last phase, the phase 4, was dedicated to tests on aviation use case, where we have a lot of activity on capitalizing on what has been extracted from the previous phases. We test the improvement we propose in the phase 2 and 3, and we had apply the generalization bounds identified on the complex use case. And now I will jump on the generalization property. So why are we interested by the generalization and what it is? So generalization is the capacity of a model to generalize, that is to say, to keep the same level of performance on average, in average on the full operational design domain versus the data that has been used to train the model. So the model is trained based on the training data, and we try to find the optimal, but this optimum is optimal for the training data set. And we need to verify that we will have the same level of performance on unseen data. Why we're interested by the generalization? It is really to demonstrate the ability of a trained model to handle real-world variability and maintain performance across different operational domains. It's where we can make the link with the operational domain definition, where we define the frame of where my model should operate, and thanks to the cascade of requirements, we can put requirements, it means metric and target, on the performance of our model. The next question is how to assess the generalizability of our model. So there is 3 main approach we have. First, we can measure the performance on the test dataset that will provide us a statistical approach on how what I've done is representative of what we see in real condition. We have the theory of the generalization bounds. So here what we can do with this tool is to upper bound the expected true risk. We can also use this theory to identify which architecture will be the best to fit my targeted task. And I can also use this theory to have a kind of guidance concerning what I need to take care in the learning assurance process. And the last one, what we can say also, is that there is some key area in the development process where I can influence a lot the generalization. So this is what I will show now in the next slide. A bit of reminder, because I was speaking about the learning assurance process to secure that we are all at the same page. So there is the three main steps that are concerned by this task. So the first one is learning process management. So it's really the preparatory step of the formal training phase. In this phase, we are selecting and validating key elements. So we have the training algorithm. Will I use a stochastic gradient descent or something else? I'm also selecting activation function, loss function. I'm also having a drive on the strategy I will use to initiate the optimization process. We are also selecting the training hyperparameter. And we are also defining the metrics that will be used for various validation and verification steps. So here really it is the preparatory phase. And we'll see in the coming slides that we can have a lot of drive concerning the capacity of our model to generalize. The next step is the training phase, where we are executing the training algorithm in the condition defined in the previous step, but also using the data which are being prepared in the data management process. Thanks to task one, we can a bit say that we are representative and complete regarding our targeted operational domain. And we are also in this phase having an activity on model performance evaluation, so mainly the bias variance activity using the validation test. So here it's really a metric to secure, or at least to have a good clue that we are not overfitting regarding the data. The last step is the learning process verification. So we are evaluating the trained model on the test data set. And here also, based on this measure, we can have an idea of where we are concerning the generalization we have on the test data set, comparing that our result with the validation and the training activities. To assess all what we have said, we have performed a lot of experimentation. So of course, we have applied the generalization bounds evaluation on a priori, meaning before training the model, and a posteriori for all the different use cases. We have also analyzed how the architecture can be optimized thanks to the generalization theory to provide a better guarantee on generalization. Also the architecture and the hyperparameter. And finally, we have also on the avionic use case some assessment concerning and comparison comparing different architecture and the data augmentation and the fine-tuning. Sorry. As you can see here, when you are locating the different experimentation on the learning assurance process, we can see that there is some activity which are related to the data management, so what we can call data augmentation, but also the representativeness of the data. We see that for some use case, it's key to have a clear assessment and a quality measure on how I am representative. And some other which are dedicated to one step, or between both, what you have in the green, let's say, where we are assessing and comparing the a priori estimation of the generalization bound and the a posteriori. So now let's jump on the generalization bounds. So a generalization bounds, it aims to provide a statistical guarantee of the gap between the empirical risk, what I can measure with the validation dataset or the test dataset, and the risk I have on the full ODD. So again, it's an average. So coming back to the discussion we had previously, and we say that with high probability, this gap is lower than what we call generalization bounds, which is the epsilon we have here. And these generalization gaps generally can depend on the architecture of our neural network, on the volume of data, also on the probability of our bounds to fail, and can be on the different weight or the optimization algorithm I've selected. So you can see the 17 or the 13, let's say, boons that we have selected. So for each of them, what we have done is to test those boons as a means of compliance to see how it can support to answer some objective of the concept paper, LMO4 and LMO9 mainly, by bounding the empirical risk. We check also how the generalization boons can support selection of the best architecture that can be used depending of the targeted task. In terms of protocol, we use different neural networks. So it's focused on the toy use case. And I will come back on the next slide, where we select and try to compare different architecture and also take into account the different assumptions we can make by selecting an architecture. We have also train and test several models, really to secure that we are covering a large range of possibilities, and we analyze finally the a posteriori generalization bounds regarding the assurance level. So the value we can obtain, does it mean anything in the context of performance and statistical guarantees? The result we can show is that a priori evaluation is a kind of pessimistic approach. Remember that the theory should remain valid, whatever, as we are in a priori, whatever the quality of the algorithm in terms of optimization and so on. So really, here we provide a valid value, but that can be a bit vacuous as soon as we are in an over-parameterized neural network. What we can say also is that the Peck-Bay bounds, the complexity bounds, margin bounds, they are all encouraging minimum parameters. And we come on that point on the next slide. When you try to apply a posteriori the evaluation, of course, you run your optimization. So you obtain a tighter bounds, which are for deep neural network with high dimensionality use case, too deep or too high, let's say, to be able to be used as a statistical guarantee. Nevertheless, one can see, and we see that in the XXU use case, that for small neural network with a lot of data to train the model, we can obtain some generalization bounds that are enough tight to be used at least in a kind of guaranteeing a certain level of performance. And finally, what I want to say is that for naive application of generalization bounds, it does not provide accurate and self-consistent means to guarantee the generalizability of the used model. So in the two tables, you can see the comparison between the different bounds applied on different architecture of neural network. And what we need to mention here is that the value by construction, by mathematical construction, is lower than 1. But what you can see is that generalization bounds which are calculated are always greater than 1, meaning that, yeah, I know that it will be lower than, for example, 127, but at the end, mathematically, I already know that. This is what we call a vacuous generalization bounds. Here again, we are in high dimensionality topic with deep neural network. So this result was expected at the beginning, and we try, let's say, to see how to improve those value. This is where I come on the table to the left, to the bottom right, where you can see for the same use case, the toy use case, so fashion means, we try to optimize the architecture based on what we have in the theory of generalization bounds. What you can see is that, yeah, great, it works well, but at the end, you can look at the bottom in terms of performance of the loss function, of performance of accuracy, let's say, we are degrading a lot our results. So the conclusion here is there is a compromise sometimes to find between what I need to guarantee and what is the expected level of performance I want. I'm presenting also on the bottom left the generalization bounds we obtained, so a priori and a posteriori, for the aviation use case. Sorry. For the aviation use case, so AVI, which is object detection, so high dimensionality, very deep neural network. Again, we can see that the value are largely greater than 1, and it's difficult to use them as a guarantee for our certification purpose. ATC, STT, so speech to text is a bit the same. The value are lower. Nevertheless, here we can mention that we have more data, and the neural network are a bit lighter. What is interesting here to mention, and it comes to the point for small neural network and with large volume of data, we can have some generalization bounds that are enough tight. So, for example, here you can see that I can guarantee with less than 1.4% that the training value that with high probability, what I will measure in terms of average performance on the full ODD will be at most what I've measured with the text data set plus or minus 1.4%. Now I will jump to the different use cases, so the aviation use cases, and to illustrate what we have done in terms of architecture analysis or in terms of data. Do I have enough data to be able to conclude on what I'm doing? So the first use case is speech to text, where we are using spoken instruction from air traffic controller. And what we want is to translate those voice instruction in text with a targeted word error rate lower than 10%. We are using here Airbus dataset, which are real air traffic control exchanges from French airports. It's important to notice that here we are in French airport only, but we are also using open source dataset for European airports. We have tested here different models, so with different architecture. So the VOSC API, for example, which have been trained on Airbus dataset only, and also open source model based on transformer architecture, where we train the model on the open source dataset, where we have a wider number of airports. The metrics we have selected is the word error rate, and we'll compare the capacity of our model to generalize regarding this metric. So what we can say after this experimentation is that we have an excellent performance of Airbus model on Airbus dataset. Good. Now, if I want to use this model on other dataset, open source one, for example, clearly degrading a lot the performance. It's not to finger point the model, it's not a good model. It was a POC, a proof of concept, which has been used to launch further project and so on. So the idea here is really to say, okay, what we need to do to secure that the project will deliver a solution that will perform properly on different conditions. So we have analyzed, of course, the potential issues. So we have overfitting that can be due to the source of dataset, to the audio quality and the model technology. Okay. So what we have done, we have analyzed also the model selection with regard to the performance, but also with regard to the real-time constraints. So where I will apply or which device I will use to run this model, which is key because up to now, I cannot imagine to have a big GPU on my aircraft. Up to now, it's not authorized. So we need to find solution or to lighter a bit the model to secure that I can succeed on achieving the targeted task. Clearly, there is an issue in terms of data representativeness here. And what we have done is to analyze different technology, different model, train and fine-tune on different data sets. And you can see on the right of the screen a big table where we compare all those metrics. Finally, what I want to highlight here is really what is at the bottom right in the table, where we can see that it's important to have the data completeness and representativeness taken into account when you train a model. So training a model on whatever you want and only testing it on one data set which is representative is clearly not enough. And you can see that in the different assumptions you have in the learning assurance process, that if you don't respect one assumption at one point, it will be difficult to use the metrics or the measure you have at the end to generalize that and to say, yeah, my model is really generalizing. So our conclusion here is really use as much as possible diversity in your dataset, a complete dataset. And of course, you can use a fine-tuned model that you will be able to accelerate a bit the optimization and secure that what you are doing or adapt what has been demonstrated as with a good performance in one domain to adapt that to another task. The next use case is AVI, so automatic visual inspection. So here we are more in object recognition. The objective is to help the operator to perform the in-service damage detection based on images. What we want is to achieve a 95% accuracy in terms of localization of the damage, classification of the damage, and also the no object detection. So 3 classes plus object detection. And for that, we are using Airbus data set from picture of surface damages, which are a bit incomplete, clearly. We don't have a lot of data. Nevertheless, here also it was a proof of concept. So we reuse the data, the models, to see how we can have an assessment of the generalization capability. And it was a good use case, let's say, to see that without enough data, it's difficult to be able statistically to provide guarantee on the performance on unseen data. Our results are presented here. So clearly, due to the limited amount of data, and especially for lentil strike, so it's one kind of damage we have in this use case, to achieve the targeted performance. We are at 41 or 62, let's say, regarding the 95% accuracy expected. So for that, we propose some activity to improve a bit the performance and generalizability of our models. So we use data augmentation. Okay, so augmentation, we say simulated data, but come back to the comment we have is more making some small modification on the image we have in the dataset, so translation, rotation, let's say. We have also modified or proposed or analyzed the gap we could have with a different architecture. So we were in YOLO v5, we go to YOLO v8, where we have a much more parameter and a kind of different approach for the loss function or the optimization, let's say. And we have also tried to fine-tune the model. Thanks to that, you can see in the bottom left table that in terms of performance of retrain completely model, the more you complexify the model. So the YOLO v8 large, meaning with a much more number of parameters, achieve higher performance. This is without data augmentation. And what you can see on the right table is that if you fine-tune your model without enough data, you cannot expect to have, let's say, a satisfactory level of performance. So really here there is a strong link between the data quality, the data volume, and the performance you want to achieve regarding the complexity of your models. And finally, I will present the last use case, which is a classic use, so collision avoidance system, where the objective is to go from a lookup table approach to a neural network approach. So the primary objective was to reduce the storage space required for the lookup tables and to use a different neural network. So I just illustrate on the right of this slide the process. So you have the 4 or 5 lookup table, which are coming from the RTCA Special Committee 147, where we split those tables in 45 new tables. And what we want is to have 45 neural networks capable to output what is in our 45 tables, but with a lighter storage space. This is a classification cross-entropy approach, and we see now the result we have obtained, that we have, again, a good performance on the model. Nevertheless, the targeted accuracy was 100%, which is, we are not at that level, and we have observed that there is another represented classes, which is clear of conflict. So to bypass this potential issue and to try to see if we can improve the model performance, we adapt the model architecture for the classification task, and we have also tried data augmentation, let's say, to solve the unbalanced dataset issue, or to use a weighted loss function. So the data augmentation has been done on all the classes except the clear of conflict one, just to have, in terms of representativity, let's say something which is more balanced. So we try to retrain the model and so on, and we measure also the generalization bounds. What we can say is that here, clearly, we don't change the volume of data, just the repartition of the data, the ratio between the different data. And in terms of generalization bounds, we are not capable to improve a lot. For the weighted loss function, so let's say when we say weighted loss function, is to minimize, let's say, a bit the clear of conflict class impact on the optimization. And here also, the results don't show a lot of improvement. Our feeling is that we did not improve the performance of the model. Nevertheless, there is certainly some improvement in terms of stability and robustness of the model, so which is not related to or completely related to the generalization, but is also a key criteria that has to be taken into account in the certification process. So as a summary, I will say that during the learning process management, we have the possibility to influence the generalization. So the model architecture selection, where at the end we are making some assumption by making a choice of an architecture. For example, if I choose a convolutional neural network, I, by assumption, say that there is a symmetry in the data, saying that if I have a translation of a small rotation, I will not change the result of my neural network. So this is one clear assumption that has to be taken into account also when we do the evaluation. There is also the metric selection. Some metrics, when they are not properly selected, can reflect something different than what we are expecting in the targeted application. So hyperparameter selection is key, and the volume of training data. I did not mention or show an experimentation what we have done, but we can see that depending on the volume of data, you can achieve a certain plateau. But at the end, when you try to increase artificially the volume of data, so meaning that you augment the number of data without taking into account the data representativity and completeness, then you can degrade a bit your performance. And this is mainly due to the fact that at the end you are no more in the ODD you defined at the beginning for the training data set. For the learning, the model training, let's say, it's important to mention that there is a learning curve analysis, which is important. It can help us to identify when we are under or overfitting, and also take into account the convergence stability during the optimization process. And at the end, for the learning process verification, the a priori generalization bound can be used, but will be efficient only for small neural network with a high volume of data. And the performance can be measured empirically to the test dataset. There is some issue and limitation we have observed in the development process. So clearly, we should take care about weak data processing and also to the assumption we are violating during the development process. Also taken into account the volume of data needed to train a model. We have also to take care about the gap we can have between selected performance on the training objective versus what is the industrial needs. And finally, the model selection, the architecture has to be designed with regard to the detailed result we can have. If I take a classification issue problem, let's say, to secure that at the end I don't have a class which is underperforming regarding the others. And here also, certainly, we'll have some compromise to take into account, making the link with the discussion we had yesterday with the ethics approach, securing that, yeah, we need something representative, but at the end, we don't want to have any ethics issue. So, as mentioned, there is compromise between representativity, completeness, but also we can mention the ethics approach. I think it will be important in the future. So mapping the conclusion on the learning assurance steps, what we can say is that for LM04, the generalization bounds are difficult to use them a priori, meaning during the learning process management, when we have a deep neural network and low volume of data. Nevertheless, for small neural network, we can achieve something that can be usable, let's say, for statistical guarantee. And it's important for the developer to take into account this guarantee versus the result he's expecting. There is some methods that can be used at that level. It's raining a lot, to boost the generalization, so such as the generalization, the penalty method, and the data expansion. For the model training, so an important point to take into account is really the learning curve management. This can support to answer the LM07. For deep neural network, it's clearly a key indicator concerning I am in an overfitting mode or not. As the generalization bounds cannot be used, it's important to identify what other kind of measure I can use to try to answer the objective. And also the convergence stability, for me, it's an important point to secure that at the end for each epoch, I will go step by step and not having something which is completely noisy and will be by chance that I succeed to be in an optimal local minima. The training objective and evaluation already mentioned. And finally, for the learning process verification, so the generalization bounds verification on the trained model, again, same conclusion than the a priori evaluation. So for deep neural network, we can succeed to achieve a tighter bounds. Nevertheless, they still have back use when we have in high dimensionality, deep neural network without a large volume of data. But there is some values that can be used for the learning assurance process when we are in a small neural network with high volume of data. In terms of performance, so the statistical tests we can do on the test data set need to be taken into account carefully to answer the LM09. Again, there is a strong assumption, which is that my data are representative and complete regarding the ODD. If not what I will measure on this test data set, it will be difficult to say that it is valid for the full ODD. And the trained dataset quality is also important to take into account. Remember that there is a strong assumption, which is the IID, so independent identically distributed data, which flow all over the learning process management. So it's important to take that into account. And for the LM14, so empirical gap measurement is a good indicator, and but we need to also have issue detection in terms of analyzing deeply my result class by class or for the different kind of condition defined in the operational design domain. And I thank you for your attention.
Thank you, Jean-Baptiste, for presenting the outcomes of the task 2. It is now pouring down, but it's not on your hand. So just let's continue now with the Q&A session. So 20 minutes. Maybe before we address the questions asked on the Slido, we can maybe take questions from the room. So maybe just raise your hand and turn on the microphone in front of you and just address questions if you have any. Sure. Stefan, are you in the room?
Yes, I'm just over there.
You didn't clearly define what is a priori and a posteriori. Can you be more explicit?
Yeah, sure. So a priori is when I do the evaluation before the training phase. So during the learning process management, and a posteriori is when my model is trained.
And what is the consequence when you know the model? What is the impact on the bound?
We achieve clearly a tighter bounds. Why? Because I make some assumption at the beginning. The assumption should be enough wide to secure that I can cover all what will happen during the training phase. So a priori evaluation is really pessimistic. A posteriori evaluation, I have the weight, so I can really calculate the distribution of the weight of my neural network, for example. And here I have clearly a tighter bounds because I remove some assumption which was degrading the value.
Then I ask my second question, like that it's over.
Yeah, please.
What is the difference then between a posteriori evaluation and the standard statistical estimate based on the sample for an estimation of the mean or the quantile? What is the difference between?
So the difference is clearly the generalization bounds is based on my model, my data, what I have. I can say with a high probability that what I will measure on the full ODD, which is not accessible, can be upper bounded by what I measure on empirical data with my test data set, plus a certain epsilon, which is my generalization bounds. So we are not speaking about the same statistics. So you have a statistics which is based on my data, what I can achieve, how my measurement is representative of what I will see. And the second point is based on the theory, some assumptions. I can guarantee that whatever the data you are using, the result will be lower than a certain value, which is my generalization curve.
Okay, thank you.
Yeah.
Can you hear me? Yes. Antonio Monzon, Airbus Defense and Space. I have a general question. Generalization is for me a distinctive characteristic of machine learning compared to other types of algorithms. And I think it is especially valuable for the adaptability in general, which is quite important, especially in changing environments or in a kind of a tactical situation. I'm thinking in my business, which is more military application. Have you assessed a potential correlation between generalization guarantee and adaptability at all, or have you thought about that?
No.
Okay. Maybe.
No, I was thinking about that. For me, there is also, as discussed this morning, the generalization or generalizability is really a measure of the average.
Mm-hmm.
So you can adapt, but if you can guarantee that the average is the same, is good. At the end, what you are expecting is maybe not that. It's really to have the average, but also a very small standard deviation. So here, I think maybe Arnaud could help you with the task 3 to answer this question.
I understand that it is tricky, but I'm also thinking out of the box, because at the end of the day, I need to sell also when I have to promote the usage of ML, I need to promote what are the added values. And I personally see that here is a big added value to be used. Okay, but that was all. Okay.
Yeah, and the frame of the project was really,
of course,
supervised machine learning, machine learning or deep learning.
Thank you.
Okay, let's take question from Slido then. So how is the link between data completeness, which is task 1, and generalization, task 2, explored? The need to handle unseen data clearly relates to data completeness.
Alors, the need to handle unseen data clearly relates to data completeness. So, sure, but the link between the two tasks, first, when you are making your measure, the metrics are also regarding some assumptions. They are valid in certain conditions. So if you don't have the completeness or the representativeness of your data, it will be difficult to use the result to generalize, say generalize, but let's say to use this result to demonstrate something on the full ODD. So you need assumption, statistical one, which is the representativity and the completeness. Maybe Thierry, you want to add something?
Yes, in fact, concerning the use of the data that is not used in the training to evaluate the generalization. So this is more for the generalizability of the model, its ability to have same, let's say, accuracy, for example, as we have noticed during the training of the model. But regarding the completeness, I can see that it is another kind of generalization, because it is not comparing the data seen on the training and the testing, but it is more about, let's say, having a wider definition of the ODD, because here we started from a high-level definition of the ODD, and we assume that on the target data that the model will be seeing, there will be that and this features, and we evaluate the generalizability regarding this kind of features.
Stefan, did you have another question? Okay. Okay. Okay, so do generalization guarantees hold under certain assumptions, such as the new data is from the same distribution as the training? In that case, do you check that?
So we'll not call generalization guarantee, because behind generalization guarantee, you can have different means to succeed that. At least for each means, you have some assumption when you can use it or not. For example, generalization bounds. In the theorem, mathematical theorem, we check systematically if we are always in the assumption covered by the theorem or not. So, and yes, clearly the distribution can be 1 point, but after you can also have some mathematical approach to say, yeah, my result remain valid if I'm a bit shifting the distribution. So here also there is some active research on this topic to deal with out of distribution guarantee and so on, to secure that at the end we are not only focused on one specific use case, which is too strict to be applied out of on the real world.
Dimitri, I saw that you had a question. Do you want to address it?
Yeah, thank you. So I was wondering, so you said that generalization bounds can be tight enough for low complexity neural networks with large amounts of data. So can we speculate for deep learning? Can we assume that we have these large amounts of data? I don't know how, but in this case, would you say that the bounds would be tight enough, same as for the low complexity, or there's some additional barrier?
What we saw in the AK6U is low dimensionality, so only 5 input, okay, different input. And the deep neural network, or the neural network, let's say, was only 6 layers. So clearly, as soon as you will increase the dimensionality of the input, you will increase a lot the number of data needed to cover statistically properly your ODD. And this has a strong link with the generalization bounds. Generally, you have in the squared under 1 under n. So clearly, the complexity of your model will drive clearly the volume of data you will need. And the complexity is also depending of the dimensionality of your input space. So to answer your question, when we test on deep neural network and so on, the generalization bounds was requiring 10 million of data, for example, to succeed at least to achieve to be close to 1, which is not enough for us because we want to demonstrate that the gap can be closer than 10%, 1% or things like that.
Okay, so how do you measure the data dependency on aircraft configuration? What about future AD or service bulletins about AI data? How will they apply track?
I will let you answer, but I had the same question recently in the certification project. So knowing how the data depend on aircraft configuration is indeed...
For the AVI use case? No.
No, in general, what we are seeing is system manufacturer preparing a given solution for a family of aircraft. And one of our concern is to know if the application in question is working on a given model, but also on a very similar aircraft, because we have often certification application covering a list of models. And to give a bit of, I mean, we are not explicitly covering the topic in the EASA concept paper. One argument could be to explain that the way the system works is not affected by changing the aircraft or the aircraft model, the aircraft configuration, because the type of data that is captured is not aircraft dependent. That's one solution, but then I don't know if you have other insight.
Yeah, for me, this is crucial and has to be determined also in the ODD definition. I want my solution to be valid for the different aircraft. And when you speak about configuration, there is also the type of paint you will use, the color, and so on. So here, when you speak about aircraft configuration, there is plenty of things that need to be taken into account. Is it still valid if I change engine? Is it still valid if I change, I don't know, the options the airlines is buying. So for me, this is a key point that has to be partially addressed, at least in the ODD definition. And for the service bulletin and the AD about AI data, so
for embedded system, we have already a mechanism in place to implement AD or service bulletin. This may not change fundamentally. However, to implement the continuous safety assessment in other domains of aviation, there are indeed a set of objectives today in the concept paper, and we will have some work as part of rulemaking, as part of the ongoing rulemaking task, to precisely define on how we will control the equivalent of AD or service bulletin for other domains of aviation. But that's a good point. It's true.
Okay, a question about AVI. So how do you know that the poor performance is due to limited training data set? Lightning strike may be easy to augment.
Alors, so the second statement, lightning strike may be easy to augment. No. It's completely the opposite. At least the dance and so on, after discussing with Stéphane Guillon, who has worked a lot on this use case, clearly we don't see so many lightning strike defects, at least in our Airbus position. And for the dance, at least we know structurally how it is done, so we can use simulated data, let's say, which will be representative and so on. But we come back to the one question that could be also in terms of data augmentation or data simulated, how to secure that we are a complete representative of what we will see in the real world. So how do we know that it is mainly due to the poor volume data? Because we really have few data. So it was easy to finger point this issue. On top of that, the state of the art concerning the different benchmark of the architecture we have selected has demonstrated that for the same kind of task, the performance we measure at the end of the training phase was very far to what we can expect.
Thank you, Jean-Baptiste. Let's continue. So do you think that with the present rate of progress in generalization theory, we will obtain a non-vacuous bounds for realistic virtual tasks in 3 to 5 years?
For me, we are missing some mathematical means to go further. So maybe in 2 years, somebody will come with the new mathematical means that will help us. That's, to now, I'm not a mathematician and I'm not fully involved in this theoretical activity. So what I can say is that up to now is difficult. I hope that yes, we'll be able to have that. And if not, we need to prepare to have something else to measure and to provide guarantees. Because what we want at the end all is that to secure that what we are developing is working properly in the real condition.
Can you give any recommendation on how to handle justified training VNV data in case models based on physical equations were used to create those data?
I don't know.
So I think this is just an example about how the synthetic data was generated, but this question can be generalized for all cases where the data is generated automatically and we are not working with the real data. So this is very difficult to answer directly. In fact, we need to do extensive analysis about the methods that have been used to generate that data in order to say where exactly on the VNV process and all the development process of the AI can be enhanced if there will be some problem sources related to the performance that come from the VNV process and not from the methods used to generate the data. I think here we need to review first the methods used to generate this data.
Remember also one point. What we want to demonstrate. We have requirements. Up to now, when you are in a rules-based approach, you can link the requirements with line of code. Now you have a bunch of data. You say that the knowledge is within the data. I train a model, and I expect that all the knowledge underlined by the data is captured in my model. So here the recommendation is really secure that the knowledge is within the data. You have a good data quality, or you have a huge volume of data, because there is a relationship between the optimization and the data quality.
So is the assumption correct that explainability would support generalization? If yes, why are such tools not used?
Again, generalization, we measure the average performance of the model on the full ODD. Explainability is, can I justify one result? So I think there is a relationship, clearly, but let's say we have plenty of models which are very difficult to explain how they are working. Nevertheless, they are developing very good level of performance in terms of generalization. So I don't know if you want to add something, Thierry or Xavier.
Yes, in fact, there is a room to use outputs from the explainability in order to support the generalization enhancement. Because as presented by Jean-Baptiste, there were some alternatives considered during the project in order to bring better results and improve the generalization. So if we rely on results from the explainability, that would help to understand why the model is providing that poor result, why this specific classification is not good, why this specific error. This would help us to understand better where the model is more likely to make mistakes, and hence give some insights for the data enhancement, but also the model architecture. So it is not directly related only to the generalization, but also to the robustness and also the data management.
Okay, one more questions. So those values greater than 1 are probabilities. And when you give those probabilities, have you tried for less but feasible accuracies to reduce these probabilities?
So thanks for the question. I think then we need clarification. So the value of generalization bounds is not a guarantee, it's really a value. I guarantee that a gap between two values is lower than a certain bounds, what we call generalization bounds. So the value you saw were greater than 1, but it's not a probability. I just say that my generalization gap, the gap I have between the true risk and the full ODD and what I can measure based on the dataset available is lower than a certain value. The probability that this will happen, we take that as 95% by default. So only 5% risk to achieve these generalization bounds. And yeah, clearly, this probability of not achieving the generalization bounds is part of these bounds himself. So there is a relationship, but the value we have are not probability at all. And the probability are taken into account that with high probability, I say more than 95%, I can guarantee that I will have this result.
Okay, time's up. So thank you so much, Jean-Baptiste, for the presentation. So
thank you.
Yeah, thanks. So
how do I get back in? You just need to. All right, should be working. Yeah.
So Arnaud from Numalis will be presenting the main outcomes of the task 3. So Arnaud, floor is yours.
All right, thanks. So hi everyone. So I'm Arnaud Yoren, I'm the CEO of Numalis, and so I'm going to try to give you a large presentation of the result we obtained in task 3, which was about robustness. And so we had several subtasks that was in the tender. So most of the first task we've done was regarding the review of these concepts across both the EASA documentation, but also elsewhere. And then we'll delve into directly the use case we used, both the toy use cases and also the avionic use cases that was presented this morning. So first of all, why talk about robustness? So from an external point of view, robustness is an important part of, for example, the regulation of the AI Act. It's one of the pillars identified by the high-level expert group that has produced the documents underlying the work for the regulators. And it's a key requirement of the standardization request we received as a CENELEC also. So there is a huge push for regulatory documents regarding robustness, and also in EASA, it's also a key issue that was underlined by the EASA concept paper. So there is alignment there, and this is why this is a key topic to address today. But why robustness specific to AI? AI, as we saw just before, has this generalization property that is quite appealing. This is basically why we're doing AI. It's because it's able to generalize. However, since we're dealing with unknown data and a capacity of generalization that is not fully understood and not predictable, easily at least, then robustness came into play, because I want to be able to generalize, but I want to also have some boundaries on how much it's going to generalize and how much it can be wrong. And so this is why we have this trade-off to find between generalization and robustness. And from the EASA perspective, robustness is described in the EASA concept paper through 3 main requirements: LM 11, 12, and 13. That will be, you know, the red string we're going to follow across all the presentation here. So we are very familiar now with the W cycle, so I'm not going to delve too much into that. I'm just going to give you our understanding of what are the LM 11, 12, and 13, and what are our opinion when we started the work on these. So LM 11 is basically, I want my training algorithm to be stable. Basically, if I'm going to put the same blank neural network and the same data set, I should have the same output. It seems fairly innocuous to say that, but it's also, I want him to be stable. So if I maybe just remove one point in my data set, it shouldn't, break the whole process. It should be kind of stable. My neural network at the end should be kind of the same. And here we'll see that it might be more difficult to achieve than we thought, because like we're going to demonstrate, this kind of property were never envisioned by the people who build these training algorithm. And so we're probably asking something that might be difficult to fulfill. LM12, we want to have a stable algorithm. So once my algorithm is trained, I want it to be stable. So if it's saying like this is a plane, I want this decision to be quite stable across the possible variation of my input. So here we are known territory. This is a very classical requirement we want on software. And so basically we're assuming that it's going to be kind of easy to implement and maybe to verify. Finally, LM13, I want my train model to be robust against particular non-nominal events. So here we're going a little bit on the fringe of the nominal cases we have, maybe some rare events or corner cases, edge cases that can occur within my ODD or at the fringe of my ODD. And I want to be able to verify that my system will still hold. It will not break easily under these conditions. So here again, maybe it kind of be harder because, if you have a very large ODD with many attributes, it might be not easy to cover every corner cases there, because there will be an exponential number of ones. So it might be difficult to implement. So you're starting to guess that, okay, so there is different level of robustness we want to assess. So there are the nominal cases. Okay, so performance metrics will be able to challenge that probably. There is also variation of the nominal cases. So maybe my plane is just not this plane, is maybe a red one. So how am I going to verify on red planes my system is working? So this was basically the question, I think, this morning. What about the red ones? So I didn't anticipate this one. I can have also this kind of weird cases where machine learning can be sensitive, so adversarial attacks. So basically here we're not exactly in robustness territory, we're more in cybersecurity, but still kind of the same. Like my input is kind of different. Now it has these weird patches that might cause an adversarial attack. And so this might not be classified as a plane, but maybe as, I don't know, a car. Or there will be completely out of the domain example, like non-existent use cases like plane with 3 wings or stuff like that, that I'm not maybe want to consider these under my robustness assessment. So I need to find where I'm going to stop there. I need to be as thorough as I can to convince the EASA that I'm working well, but I also need to be practical and not considering everything out there. So in order to help me, EASA has this nice ODD concept that I can use. So I can say that I know very well the nominal working domain my system is going to operate, given though I need to still describe my ODD, which is not an easy task sometimes. And then I can go more on the outside and going into robustness territory, or even resilience territory, or system failure territory. So basically, the more I'm going outside what I'm supposed to operate in, maybe my system will break. And so I need to assess across this spectrum whether or not my system will be working. So basically, if now I'm going to the literature, I'm going to find roughly 3 types of methods to address that. Statistical one that are widely known by every AI engineers across the planet. Formal one, less known, more going to gain some speed now. And empirical one, if I'm not knowing the previous 2, well, at least I have that. And so if I'm going now into the literature, what we've done is we try to align as best as we can different sources of documents that are kind of want to treat the same concepts as robustness and stability. And so we delve into the ISO documents on the SC42 subcommittee, where I'm the editor of several documents there. We read thoroughly also the EASA, obviously, concept paper. And we had also access to some of the documentation from the WG 114 through the EASA in order to see how much this concept can align. And the good news is that there is a lot of commonalities between these 3. Not always. Sometimes the concept of robustness is going further on one and not the other. And so there are some parts where we need to maybe exactly say from which point of view we're talking, but basically the basic ideas are there and they are probably aligned. Also, we went into a study of the maturity of the tools that are able to match these concepts, because it's nice to have a good idea, but it's better if you can put it in practice. And here we try to see from either the scalability of the methods and the applicability on the different use case we had. This was the 2 lenses we tried to apply in order to see whether or not this is going to be useful. And the overall conclusion was to really try to apply that as much as we can on the real use cases we had from the Airbus partner. Right, so if I'm analyzing the literature, basically I'm going to see these kind of requirements all over the place. So stability, I'm also going to see the measurement of biases, variance. I'm going to see, for example, also properties like relevance that ties more to explainability. And I'm going also to see properties like reachability. Is my system able to reach a certain state I don't want him to reach or not? And so we can express these properties mathematically. We can define the requirements on that. We can put thresholds on that. So that's basically good, because now once we have that, we have specifications. And so with specification, then you can go towards verification. And so for verification, our first take was to say, well, not one technique will be able to cover everything. We have to be honest on that. There is no magic one to say, I want my system to be robust, and in one go, I'm going to verify that. No, that doesn't work because the requirements we want to test are very different in nature sometimes. And so different techniques will be better suited for each one. And so what we think is that combination of techniques will be key in order to, like I said, try to cover as much as possible the scope of robustness we want to cover. And so we assess that for nominal cases, formal methods will be great because we have a clear mathematical space we want to verify. We know the data points within it. So formal should be working pretty well. And the more we want to explore and go to fringe cases, statistical is going to be great because we're going to, explore and send data points across the ODD and see what's happened. Whereas, formal methods are less likely to be able to explore large, very portion of the output space, And finally, empirical is the best way to explore the very narrow, very specific, critical, scenarios where only a human mind can imagine the weird condition on which the system can fail, and have the very specific scenario to really stress test the system. But all of that needs to tie to the ODD definition. Without that, that won't happen. And here, for many use cases we had, we didn't have an ODD at first. We tried to, bring one as we go, but it's a very hard process. And lucky for us, we're not the only one to have this problem. Automotive are also the same one, and so we can probably have, cross discussion with other sectors that have exactly the same problem. So methods will be applied in complementary way, but we will have probably problems of scalability because not all methods are easy to apply apply repetitively or to scale. And so here there will be probably in the next years a lot of efforts to improve some methods in order to make them scale more easily. So basically, the trade-off is as in this graph. You have in one hand the confidence level of proof you want to have, and the other axis you have the complexity to put it in place. And so obviously empirical methods are kind of easy to set it up. You just need to have like a good brain and some time, but they won't cover much ground. So the confidence you're going to have is rather low. Statistical, rather easy also to set it up, give you more confidence. And the most difficult one to set it up is definitely formal methods, because here you need to have like tools, you need to handle the tools, you need to understand how to do it, you need to know how to interpret the results, etc. And they take a much more time to process than the statistical ones. So definitely, you will have to mix a little bit of both of the three in order to have something coming up. Right. So, like I said, we have also this this notion of we need to explore not just on the nominal cases, and so we also did a work inside the deliverable in order to see how we can define corner case exploration. And here I was just saying before that we should benefit from discussion with, for example, the automotive industry, because there is a lot of work done there, for example, in order to define at different conceptual level what are corner cases. And so probably here, even for the aeronautics sector, we can draw some knowledge in, because for example, for them, they have some form of ODD also. But they can say that, yeah, I have some corner cases appearing at, the camera level, like some pixels are going wrong. Or maybe at the scenery level, the weather can change. Or maybe at the object level, the objects are not the same as before. Or even the different scenario unroll differently, like suddenly I have a skier or not, or maybe I have a weird light in front of me. So they have these layers of semantic complexity of the corner cases that we can bring in also for us in order to describe more when we want to explore the corner cases. So finally, what are the three approaches? So, like I said, we want to combine all of this in order to make something, as much covering as possible of the input space. So statistical, basically, we want to scatter points across the ODD. Formal, we want to verify locally some property, but when we're sure a property is true, it's true for everyone within it. And so we want to have like boxes where we want to be sure that on these boundaries, I know my property to be true. And empirical, we want an expert to say, I want to test these particular cases because I know these cases can challenge my system in a weird way, and I want my system to see how it reacts. Obviously, this brings some discussion because for statistical approach, rather easy to set up. You just have to test the system, but you need to have the data set. That might be a challenge, like we see previously in task 1. If you don't have the data, you kind of stuck there. For formal methods, you only get local guarantees. There is no yet, I hope maybe in the future, but there is no yet global guarantees that you can apply on large, for example, neural networks. But it's very good at tackling high-dimensional subspace. So even if you have like millions of dimension, you can at the local level have a property. Whereas with statistical, you cannot, explore everywhere in every dimension at once. And for empirical, definitely you need to have a protocol. So you need to have people to review the work of the people who work. And so you have this whole chain to be set it up in order to have something that works, which can be painful, but allows you to explore. And so what we've done is we're trying to see on each property we want to verify that was described in the different documents, whether or not a particular methods would be suitable or kind of suitable, but with some difficulties. And so we came up with this table, which is not perfect. We will change, I hope, in the near future because some of the technology will advance and maybe some cell will go to pink to green and etc. But at least it shows rather easily that we can cover probably everything in terms of property with a combination of methods. And that was ultimately what we were hoping for, because if there is one property that it's not covered by anything, then we have a problem. And so basically, like I said, we have formal methods to do local results. We have statistical that can do sampling across the output space, the input space. And we have empirical that requires human intervention. That's the main drivers of each one. I'm not going to delve into each of them, but during the presentation on the use cases, you will have more example of exactly what we meant by this. I'm going to cherry pick some in order for you to understand what we've done. So regarding the use cases, so basically, we have the toy use cases, which are kind of open source, kind of small, interesting, neural networks we can verify, and also the avionic use cases. So here I'm going to focus not on everyone, but only on the one that are not in gray. So the first one is a classifier of images, which is kind of small. That comes from the aerospace. And on this one, we were able to test the three requirements, LM11, 12, and 13. I'm going to also to focus a little bit on the healthcare one, which is also a classifier, but not of pictures or time series. So time series is here more to give you some perspective on neural networks that might be applicable, for example, for maintenance. Which I think most of the room here are interested in. And so this is why we selected this one. And here we were mostly playing with the LM11 and 12. And on the avionic, I'm going to detail a little bit what we've done on the detector, so the AVI, and also on the speech-to-text, STT. Why these two? Because, well, these two are the most, the biggest one we had. AK6U was not, the most maybe interesting one because it's well known, whereas these two were kind of new, and so we definitely want to share it with you. So first one, classifier of picture from the aerospace. So basically, it has to say whether or not there is a crater on the picture because you are going to land a space probe and you want to avoid craters because craters, they are not smooth, and so your space probe might crash. And so basically, it's a use cases based on the images of the Rosetta mission, which is public, so you can play with it. And we made a very naive convolutional, neural network with some convolution, dense average pooling, something really, nice and easy. It's probably like 50,000 parameters or 100,000 parameters, not more. But it achieved fairly good, accuracy, so we're happy with that. On the UDD, we were interested to define what would be like the kind of images we have, and well, basically in space, a lot of can happen. So it's really not easy. When you see the Rosetta pictures, there is a lot of stuff you're not expecting to see in the space, but it is. And most of it, what we've seen is that there is kind of defects that are really not very helpful, and so we identified that there is flares. So these circles into the pictures, And also in space, you have gamma radiation that are hitting you all the time on your sensor, and that causing that kind of weird, arrow inside your image. So that's the setting of this use case. So now let's see what we've done regarding LM11. So remember, 11 is stability of the training process. So I want to have kind of the same neural network if I was to remove a little bit of my training set. And so what we've done here is basically, since it was very nice and small neural network, we can, train it a lot of times. And so what we tried is to remove one by one or by percentage the number of data points we have. So on the left, basically we remove just one example on a training set each time, and we verify how much the accuracy is changing. And so what we see is that most of the time the accuracy is kind of the same, except sometimes you remove one data point within the thousands we use, and suddenly your system just crash, and you lose like almost 20% of your accuracy, which is not ideal. This is not stable. This is not what we wanted. So here, first word of caution on this LM11, it might not be easy to set it up and to enforce. On the second one, what we tried is to remove gradually more and more data points within the data set. And so at first on the left, you have all the data set, and then you remove 1%, 2%, 3%, etc. And so you can see that sometimes you remove like 10%, you drop in accuracy, and you remove 15, you go up. So it's rather counterintuitive. You would expect to have like a nice, degrading curve telling you that, well, the less data you have, the less accurate you will be. And that would be, kind of what you expect. But that's not the case here. So again, LM11, kind of hard to grasp whether or not we'll be able to, do it in practice, because basically the neural networks kind of trying to adapt. Even if they have less data, they can be more performant. On LM12, on these particular use cases, we try different approach using formal methods. So like I said, it has 95 plus accuracy. So the training was fine, but so I didn't put the confusion metrics there. But what were interesting was, is this stable if I'm using, abstract computation, for example, to measure it? And the answer was rather no. Basically, we can demonstrate that the system is not able to keep the stability if we were to modify more than plus or minus 2 on every pixel. And so even though the system is quite, accurate. So that was kind of, a disappointment. We were hoping that the system will be more stable against this kind of perturbation. But then we ask ourselves, okay, but when I'm moving all the pixels at once, maybe I'm too pessimistic. Maybe I should verify whether or not my system is stable against particular perturbation. And so remember, we have these two perturbations we identified, the flares and the irradiation. And so we model that using formal methods in order to see whether or not the system will keep having the same accuracy or not against this particular perturbation, not something that affects all pixels, but only pixels within the range of these. And so here the results were quite different. So for example, when I'm measuring the performance of the classifier against the flares, I can see that my accuracy stays a lot more until I get to plus or minus 10, so like 5 times greater than what I have before. However, what we distinguish is that depending on if the images have craters or non-craters, my stability is completely different. So my system is fairly stable when it comes to crater images. It handles flares rather easily, but if it's non-crater, it doesn't handle it at all. So we can see here that maybe there is bias. Even though there is 95% on both classes, stability is not the same for both classes. So maybe there is biases there. Same thing with the radiation. But here, we were even able to go to plus or minus 255. So basically the whole range of the pixels. And so here we can say that for crater images, one radiation in 80% of the time on crater images doesn't change, even though I can put whatever I want on the pixels. So, and we have the same on non-crater, which is caving a lot faster than crater images. So we have now this intuition that probably, one, there is biases inside our datasets, and we should investigate why crater and non-crater has different behavior. But also we have different behavior against specific perturbation depending on the ODD we're considering. Right, so this is for the first one, a small classifier of images. Now let's go to time series. So here it's from the healthcare sector. So basically it's a heart rhythm classification, whether or not you have a nominal classical, heart rhythm that looks like the one in the middle, or you may have a defect on your heart, causing your heart rate to be different than the others. And so here we have also a very simple architectures. So it's a bunch of convolutional and ReLU blocks, and we have 4 blocks like that, and dense architecture at the end. So really easy, really well known, nothing fancy about that. Also here, when we try to define the ODD, what is the right heart rhythm? Okay, no problem. We have like mathematical equation for that. What is an abnormal one? Very hard. Every person that has an abnormal heart rate has a different one almost than the others. So medical experts have different classes, but within the same classes, you can have like widely different shapes occurring. So not really easy also here to describe what is the right ODD of your system. So here we started by obviously start with confusion matrix. We had, we have more than 90%. Sorry, the image is cropping the text. We only have like one classes that has like a slight decrease in accuracy. And so we said, oh, that's weird. Why this one? And so we said, all right, so maybe we have fairly good accuracy, statistically speaking. Let's look at that formally. And so what we tried is that for a given of perturbation level of the input space, we want to verify stability for all examples for all classes. And we're going to see class by class. And so basically each pairs of lines are whether or not the system is stable. And so what we see is that for the class 3, which is the one that has a slightly decreasing accuracy on the confusion matrix, we observe that there is a huge instability occurring at a certain level. And so, oh, that's weird. Why this class in particular? And so we're asking ourselves, maybe there is something wrong with that. And so what we've discovered after the fact is that if you delve into the unstable example on this particular class, you end up having wrongly annotated data, and a lot of it. And this was an official data set from a paper published in a medical conference. We didn't invent anything of that. We just copy paste from their conference. But they have dozens of thousands of data into the data set, and so we were able to identify that after the fact, after the training, after the statistical evaluation, you can still discover errors that coming from the data preparation. And so here you kind of see why we're talking about the interplay within the 3 tasks. Because in task 3, we can suddenly discover something that should be feeding something to the task 1. And so improving the data preparation. So this is the kind of stuff we discover by trying to apply the different requirements from the EASA within the consortium. Now let's go to the real big examples on the avionic use cases. So AVI, so it's like it has been shown, it has to detect defect, so lightning strikes, dents, something like that on the plane. And basically, it's a YOLO architecture. So YOLO, for those who doesn't know, are kind of big neural network. It's not that easy to process. There are usually 10 million, 20 million parameters to that. And we want to try it on every LM11, 12, and 13. So here again, we try to do the LM11. So here we were just analyzing the impact on the fine-tuning of the system, because the way this use case was built was we had first a pre-trained model, and then we fine-tune it to the the Airbus data, because we don't have like millions of pictures of planes with lightning strikes, so we use fine-tuning. And so what we're expecting is that, okay, we want to verify that the fine-tuning at least is stable, to see whether or not we can prove that. And so what we see is that for the first class, so Dent AL, the other class is Dent LB, the first class is fairly able to be stable in performance, even if you're removing data points from the fine-tuning process. For the Dent LB, on the one we analyzed, the performance was really bad at the first, so changing there was not relevant, because if you have something bad and you remove data points, you probably ended with something as bad. But at least for the Dent AL, we were able to see that the stability of the behavior of the fine-tuning was, attested. Then we moved to the LM12. So LM12, stability of the behavior. So obviously we went to a confusion matrix for, you can do that also for detection algorithm. But we wanted to also play with, formal tools on that. And so we were able to verify for each box that the detectors is outputting how much we can verify the stability of this box. So basically, for example, for this box 0, we were able to calculate, for example, how much this box can change decision in terms of class, how much the objectness, so basically it's a parameter outputted by the system to say if there is an object within it, the objectness can change. And so we were able to compute stability for each box of the YOLO system. And so that you can then, if you want, increase, the amount of perturbation you want to verify to see how much your box is going to stay stable before, breaking out, changing decision, or just disappear. So this we were able to do with formal methods. So for a YOLO v5 architecture, that's kind of new. I don't think there is a lot of equivalent out there to be accessible. And so it takes obviously a lot of efforts and time to get there, but it's doable. That's the good news. For LM13, so here we basically rely on classical perturbation that can occur and cause distortion to the image. So the fine-tuning does not contain augmented pictures with this kind of distortion. This was new for the neural network. And so we use the classical, blurs, Gaussian, vertical, horizontal, the kind of brightness, changes you can make. And we have like different levels of perturbation we want to try to stress test more and more and go outside the ODD. And so for these, what we discover is that for these 4 types of noise that we are illustrated here, basically the system performance kind of breaks all the time, rather in the same fashion. Maybe the Dent LB sometimes tends to resist a little bit more, but for the rest, we're going to a good accuracy to almost 0. And so this probably hinted us to say that, well, these kind of perturbation are not well handled by the system, basically because the system has never seen them. And so it begs the, for the designing process to say, well, we should probably do more data augmentation on that in order to improve the robustness. So here again, you can see that the interplay within the evaluation at the end towards the design to say, hey, we have to do this in iterative fashion in order to improve the overall robustness at the end. Finally, the STT, so speech to text. So this one was the most challenging. If you thought that YOLO was big, speech to text is even bigger. It's I think the wave-to-wake is 300 million parameters, whereas the YOLO is 20 million. So it's 10 times bigger. And we used two models that were provided. One is a wave-to-wake, and the other one is described within the CALDI architecture. We're definitely not able to do the LM11 because training one model like that can take weeks with a very large server. And so if we were to do that like thousands of time to measure how much the stability of the training algorithm, we will still be doing it and we're not presenting results. So we skipped LM11 and go straight to LM12. And here, what we were able to achieve is for the first time to be able to apply formal methods onto STT algorithm. And so what we're able to do is that basically you have a sound at the input, and at the output you have a sentence. And so what we want to tie, for example, using formal methods, is to do some explainability. Say, okay, so this word, this output, can you tie this to the input? And tell me what in the input has driven this word creation at the end. And so we were able to do that with our tool using abstract interpretation, considering noises on the input, so on the noises, on the sounds at the input. And we say that, okay, for example, for the word minimum, what are the instant within the sound that are relevant to do that? And so you're able to verify whether or not it makes sense for you as a human, because you can then confirm using a segmentation algorithm whether or not it's true. And so for that, on this one, for example, it's on wave-to-back. But we were able also to increase the level of noises we want to verify. So imagine your background noises is augmenting. Is my traduction still the same? And so we were able to gradually, prove whether or not of the number of the intensity of noise we're considering, whether or not the stability of the decision here, the translation will hold. So these are, I think, also brand new. I don't see many results out there on formal methods on speech to text. It's obtained at the very last minute of the project, to be honest. So we didn't have time to delve very much into how to use all of that into the LM12, but at least we just demonstrate that it is feasible to use this kind of methods on this kind of use cases. Finally, we explore LM13, and here we consider a noise fairly classical, which is basically the speed rate. So what if the person is talking much faster? Like I should be, because my time is up. And so we want to assess whether or not... Plenty of questions. We want to assess whether or not the system will still have the same translation. And so basically here, we were able to verify on the different use case, the different algorithm we have, like CALDI and wave-to-back, how they react against this type of perturbation. And so we can see that at first, the error rate is better on the CALDI algorithm, but it breaks more easily than the wave-to-back. So at some point, the wave-to-back is getting better than the CALDI because its error rate is lower than the one. We also trying to see whether or not there were specificity within the dataset, because in the dataset we have also labeled sounds from person who were German, Swiss German, or Swiss French. And so we were wondering whether or not on these particular subsets we have different behavior. And so we measured also how much these different subsets of the evaluation sets have different behavior. Finally, so in terms of takeaway, we identified 4 of them. The first one is to verify using class separation. So how much my system is stable before changing decision, how much we can assess stability. And if not, then have redesign of the system. We also explore how much from the definition of the ODD, you can model specific perturbation in order to stress test your system and verify if your system will hold against this very specific perturbation. We also used the relevance, so the explainability, to identify biases. I'm not presenting that in the slides, but it's in the report. And we can use that in order to foster more stability of the system. And finally, we showed that by using stability, we can detect wrong annotation and then improve the dataset and go back to design and try to improve the system. And I stop there. So we can keep question. Okay. No, it doesn't. Okay.
Perfect. Thank you so much, Arnaud. As you can see, there is a lot of questions. So are you ready for it?
Yeah. So it's 17 minutes. We have to.
Yeah. You have to be concise.
Some easy one to start.
All right.
Okay. So. Okay, sorry. So the first one goes like this. What are the differences between LM11 and LM12? So stability of algorithm versus stability of models. Could you give a practical example?
They're completely different. The first one is my TensorFlow routine stable? And the other one is my output of the TensorFlow routine stable? So the first one is measuring how much you can have the same output when you're retraining, and the other is basically in production, is my system will hold decision if my inputs are changing a bit.
Thank you, Arnaud. Next one. So can you elaborate a bit on the boundary between empirical and statistical methods and which aspects you consider when rating the complexity of methods?
Right. So the difference between the two is in the case of statistical one, you end up at least with a statistical guarantee. Empirical, you only end up with the confidence of your experts. That's mostly where I draw the line between the two. And the rating, well, the problem with statistical approach usually is the high dimensionality of the space we want to address. If you want to have meaningful statistical guarantee, you need to have a sampling that is up to the challenge of the dimensions you want to tackle. Usually when you tackle like millions of dimensions, the number of sample you need is astronomical and you're not able to have it. And this is where empirical kicks in, because if you cannot have the guarantee, at least you're going to explore. Formal methods are here to try to tackle that in a different way by trying to prove on the local subspace that it's stable.
Thank you. So next question, to what degree can formal methods be used to verify robustness or different network architectures? Can it be applied to object detectors?
Well, I think we just showed that. I think the question was written before we end up to the AVI. So yes, it's applicable to detectors. We showed it on the YOLO V5. We're currently playing at Numalis on the YOLO V8 processing. What we can say is that in the literature you can find formal methods that tackle images processing using, convolution or dense architecture, but you can also do it on residual architectures. For example, if you're doing time series processing, we're able also to do it on tabular data. One big limitation that is still here is about language. And this is why we were so excited to work on the STT, because formal methods on language processing is rather new, and there is not much published yet on that. And basically because the input space of language is very different than the input space of pictures. Because pictures, you can assume a form of distance between two pictures. You can compute the difference between the pixels and how much there is. On text, it's way harder, because what is a text neighbor to another one? Is it a text with just a typo? But maybe a typo introduces a widely different meaning to the text. So in terms of semantic, it's not the same as in terms of just the input. So this is why NLP is so hard to analyze right now, still at the formal methods level. But what we try to show is that there is kind of a lot of hope, because we were able to do wave to sound, wave to text. Maybe we can do the other way around now.
Maybe we can take questions from the room. So I see that Stefan, you had raised the questions. Can you turn on? Yeah.
We can if you can display it. Yeah. So yeah. Yes, a bit of provocative question. How can we do generalization and robustness proofs without a clear definition of the ODD, which is the case for AVI and ATC STT?
I agree. That's an issue. In terms of process, I think no one should start to do validation without having to do its homework first and write a proper ODD. The matter of fact is that when we started the project, the use cases were already there, and so we had to deal with it. And so we're trying to do it backtrack, but it's definitely not a good practice to do it like that. And yeah, I agree. We should do it the other way around. But for that, the project would have to first start by please make an ODD, then make a proper AI component on this ODD. And well, definitely there was no time to do that in span of 2 years.
What do you call backtrack? Sorry.
Well, I said backtrack is that we were already having the neural network and the data set, and then we try to, in reverse, guess what the ODD was. Yeah. Whereas we should first define the ODD,
so you
then bring the data,
from the
and
model.
then the neural network.
Yeah. Okay, that's something I think I already proposed, but I was burnt because it is not in the principles of VNV to define the ODD from the results.
Exactly.
So another question, I had another question in the list, but it was clarified, yes, between stability of the learning process and stability of the model.
All right.
Just you didn't say stability of the learning process with respect to some changes, of course, in the input.
Of the data set.
Of the data set, maybe.
Yes.
Yeah, thank you.
We didn't.
So it's linked to the BVTO. It links to the bias variance trade-off.
It relates to, sorry?
It's linked to the bias variance trade-off. In a way. Huh?
Yes, I agree.
Okay.
Maybe just to add some comment about the processing of the ODD, the generalization, and the robustness. As mentioned by Arnaud, we worked, in fact, on already existing use cases. So the STT use case is one of them. The models have been already developed, and the data sets was already prepared, and we applied the findings to the existing stuff, but we have identified some missing things in the data, some correlations between the performances and the data requirements. That's one of the big challenges, in fact. But as mentioned by Arnaud, if we will work in the future in a new use case, that we will start from, let's say, from zero. So we will start the use case directly. We will first analyze the need, and then the target system, the requirements of at the system level, see what will be the target operational domain. So there is too many steps to go through before the data collection, and also before the design of the domain. So when you start working like this on already existing use cases, even on the open source or internal Airbus use cases, it is not that obvious, in fact, to have a clear understanding of the ODD. That's why at the beginning of the session, we just started by the introduction of the high-level understanding of the ODD, just to scope, in fact, the upcoming experiments.
Do you have recommendation for literature which clearly explain the basic taxonomy of robustness, resilience, stability for non-AI experts?
Well, the non-AI experts, I think, is the most important part of the question. I'm not sure for non-AI experts, but what I can recommend, obviously, read the EASA concept paper. That's a given. But you can also find interesting taxonomy in SC42 in the ISO IEC subcommittee. I recommend you can read the 22989 ISO document. You can also read on robustness the 24029, which is about robustness. And obviously you can, I think, have a look to the WG114, which has also a lot of documentation. But what we tried to do in the MLEAP report was trying to combine all of that and give you, in a short 500 pages long document, an overview of the different point of view. So maybe you can just focus on this part, and that will be enough.
Thank you, Arnaud. A question from Florence. Florence, are you in the room? Do you want to? Yeah.
It was not a question, it was more a comment concerning learning algo stability on tests we do inside the DEAL project. In fact, you have a high variation of learning results depending on the random parameter of your learning algorithm. And for example, neural network weight initialization, if you have different seed each time, you have different results.
So no, it
is not only data set which have such variation.
So yeah, I didn't bring it up, but no, we were fixing always the same seed. So the first test was if I'm giving exactly the same neural network, the same data set, I want bit precision exact same neural network at the end, and that was verified. But then we were using exactly the same seed for every run. So we're trying to limit as much as we can. Obviously, we cannot force the internal allocation within the GPU and the way the vectorization is going up, but we hope that this influence was not what we were seeing in the results.
I think you have seen that because indeed we do the same thing. We fix everything we can do. We can fix inside the model initialization, optimizer, and so on, and we see this kind of variation non-explained. And I think that with TensorFlow, PyTorch, and such kind of library, it would be very difficult to fix each parameter, in fact.
I'm interested in that, so I'm probably going to ask you offline more about that.
You're welcome.
Thank you. From an aviation safety perspective, could we ever accept the ODD not being fully covered by formal guarantees? So could start our AMP guarantees even be enough?
I think this one's for you.
Well, that was one of the intent with task 3 to see how far we could go with formal guarantee and formal methods, and whether we could achieve satisfactory result with statistical or empirical methods. We do not impose, as you know, the means of compliance. We have lots of use cases. We are not requesting formal methods for all use cases. We just ask the objectives to be fulfilled, which may be challenging for some of the cases. And like Arnaud highlighted, for some of the use cases, the method used may be a combination of methods. Because formal methods for all use cases, this seems to me quite a burden and not necessarily what we are looking. We want the objective to be met.
So a few speakers talked about the corner cases. What are the differences between corner cases and edge cases in that context?
All right, so here we're using the terminology from the EASA concept paper. So basically your ODD is described by several parameters. Like I said, for example, you have like brightness and you have weather. If you're constructing a data point which is only on the fringe for brightness, it's an edge. cases. And if you're going into several dimensions at once, maybe 2, 3 or more, so weather and brightness, then it becomes a corner cases.
In the odd scale picture where you illustrated stability, robustness, and resilience, what is the formal threshold in between those concepts?
The odd scale? The ODD. Oh, sorry. So in the ODD scale picture, where is the formal threshold in between? So I'm not sure. Oh,
maybe in slide 105, no, where you have this deal.
Oh, the 3 views. I'm sorry to not sure exactly what pictures you have in mind.
I don't know. If Elgis is with us. No.
I don't know if the person is in the room.
No.
Well, what I would say that is when you explore data points through data points, you're either empirical or statistical, depending on whether you have a statistical guarantee at the end. But if you're thinking subspaces, you're in formal mode, I guess. So I guess I will draw the line like that. I'm hoping that answers the question. I'm not sure to understand it.
I think it is slide 108.
Oh, this one? Well, we don't see it, but okay. So, well, this one is mainly to give perspective on the more willing to pay. Oh, this one? No, I think I don't think this is the one I was looking. So, what I was trying to illustrate on these scales with confidence and complexity is basically if you're willing to pay more, you will have more confidence. that's exactly that. But in some cases, since you won't be able to do it, you have to combine with different techniques in order to cover much ground.
I don't know if is Giacomo in the room with us or not. No, okay. So I will address the question. So regarding the stability, have you considered how the system engineer is going to use this information?
Yes, actually, this is what I was trying to demonstrate, is that when you're measuring stability, sometimes you discover more than the measurement you have. You discover bias, you discover wrong annotation. And so as an AI engineer, I would definitely hope that they use this information in order to improve the design or the training set. So yes, this is part of the recommendation we make in the chapter 7 of the report.
So when you find a problem with the training data classification on task 3, do you read out task 1 and through, or is there retaining improvement strategy possible?
Well, my instinct would say, you have to do it again, probably. It's the same question as if you're doing some retraining in operation. I guess you cannot just trust that everything will stay the same before. We would hope that it's true, but I don't think it is. So no, I think you have to go to step 1 and 2.
Yes, to complete, it's for sure a yes, because as you will see later this afternoon, all the feedback that we can get from the evaluation of the method, so in the learning, verification, and validation, should be used in order to go some steps back to the design and also the development of the model. And if this behavior of some missing stability in the performances will not be acceptable in the business and in the target system, so yes, you should redo the tasks 1 and 2 in order to enhance the model and also enhance the data to get better. So, hi again, everyone. Thank you for staying with us until this final part of the presentation of MLEAP results. So, to understand more, the purpose of this part It focuses on gathering all the results that have been presented so far by my colleagues concerning the data qualification, the generalization, the robustness and stability of the models, and how we can use now all these results in order to put them all together, streamline the W-shaped learning process, where to put all these results and recommendations, what are the main conclusions of the project, and how we can improve more the process, allowing people to get their AI models implemented. Yes. So for the experimental part of these conclusions, let's say, we have explored, in fact, one of the common practices that can be used in order to enhance the data. We talked this morning about the data augmentation as one of the possible tools. And then in the conclusions part of the complete project, as I said, putting all these stuff together and provide a most complete, let's say, development process, highlighting the important parts on the W-shape, what are the methods that can be used, the evaluations, the verifications that needs to be made, etc. So, starting foremost from the identification of this complete process regarding to the different tasks, what are the common practices but unfortunately weak for some use cases? So these common practices, starting from having an incomplete or unclear ODD definition for some applications, for some systems definition. So this is the high level requirement. It targets, in fact, an understanding about the data availability, what kind of performances are targeting, etc. And on the second part, depending on the ODD understanding, there should be an adapted data management level in order to ensure that we have the required quality to implement the AI models to reach the targeted performances, because we qualify the data regarding to the targeted performance, regarding to the task, regarding to the available data, to the possibility to have enough data for training or not. So all this is related to the ODD understanding and having a clear understanding of the ODD, just to make a distinction between having a clear understanding and a complete definition, which is not possible for several real use cases. And one of the important outcomes also from the task 2, there is too many features, too many verifications related to the performances from the perspective of the generalizability of the AI model itself. Here are highlighted some of them, but it's not an exhaustive list regarding the overfitting, having a misunderstanding of the generalization bounds, how these tools can be used in order to have such a guarantee about the performances of the model, adaptation of the hyperparameters, etc. And in the second part of the W-shape, so we have the verification of the learning and the performance of the model. One of the important outcomes of the task 3 is related to the robustness and how the robustness and the stability of the learning, the stability of the performances of the model, regardless to the perturbation on the data set, regardless the noise on the data, etc., can be enhanced, and what kind of tool can be used. And then, as I mentioned on the beginning of this today's session, from the AI level perspective, we can anticipate some, we were able, to anticipate, in fact, some understanding, some recommendations about the AI level requirements that needs to be defined with a correlation to the system level requirements. So, having just to give more detail for each level, here starting from the data management, as I said, we drive the data management regarding these 3 main big points: having the ODD in mind, so a clear understanding and how we can define both the features, the completeness and the representativeness regarding to our understanding to what we have in mind as an ODD. And then having also the targeted performances specification for the use case that is under development, and also how we can use the model behavior, the learning behavior, the outcome from the model evaluation in order to enhance our data quality. So to redo the task 1 and 2 and 3, etc., in order to have better performance. So it is not a one execution of the development, but it is an iterative way. So on the right panel, you can see some recommendations, some clear recommendation taken from the presented results this morning, such as having the a priori and the a posteriori assessment of the data quality, relying on the understanding of the ODD, but also analyzing the behavior of the model itself. Here are some tools, so using the PCA, the entropy, using the killer. So one of the tools that have been used also the CleanLab and BSA methods, etc. And finally, have some action points about how we can enhance the data. For the objective of the experiment, the experimentation across the different tasks, we have considered the augmentation, which is one of the possible tools. And then on the second step, how we can drive the model development and training, this to boost and to have better generalization of the model, but not only. As for the data enhancement, we can rely on the ODD understanding outcomes, but at this point, regarding the performances, it is more about having in mind the elements that can enhance or maybe harm the performances of the model in the target system. So have this in mind in order to consider it, to drive the model design by taking into account elements regarding the complexity, the dimensionality of the data, such as the VC dimension that can help to determine what is the best complexity for my AI model in order to reach the objective from the performances, but also in order to cover the task complexity. There is also a focus on the target performance objectives from the industrial point of view. So this one and the later one anticipate ways to enhance the performances. So these 2 points are the most important things in order to bridge the gap between the experimentation and the real, let's say, KPIs, and which means more having the real performances definition from the point of view at system level, but also the business, how they can see your good accuracy, your 95 accuracy, how this can be interpreted and accepted or not on the business use case. So these are some elements about the generalization, but also can apply also for the robustness, which on the third outcome reinforce the model robustness and stability. And here again, the most important actor is the ODD and the data, because the performances are really correlated to the data quality, the volume, what kind of perturbation the model is allowing, at what point of, let's say, perturbation maximum, and also having the diversity on the data, or maybe what kind of most important data points that can influence the performance and the learning behavior of the model, etc. So, as I said, one of the common practices in order to enhance the data quality to get better performance on the model and in the second iteration is the data augmentation. Yes, it is one of the common tools, but how these can be used, in fact, on the real use case here the experimentation was driven on the fashionist, which is one of the toy use cases. So as you understood, in fact, by the presentations of my colleagues, so it takes too many time. It is very complex to run all the use cases in all the data across all the tasks. So it takes too many time because we did too many experimentation. So this is one of the cross evaluations that we can have in order to show the impact of the data augmentation as one of the tools to enhance the coverage and the representativeness of the data set towards here, let's say the ODD, the overall ODD of the task, classifying in a correct manner the different images on the data set. And then in the learning management, so for the augmentation here, we considered some rotations, some random modifications of the images. And then the same data was used in order to train the same model regarding the original data set comparing to the augmented one. And what we notice here is that the augmentation have helped considerably reducing fast the error margin and help the model learn better. So from the generalization perspective, this is a good point. In fact, it helps. And then on the robustness evaluation, so which is made on the task 3. So we also noticed that the data augmentation have helped the model being more robust, even if for some data points, so there is less impact than others, even if there is some more than 90% of the data have been removed, but the model have gained in robustness and in stability. So this shows how, in fact, the data volume enhancement help reach better performances on the generalization, but also on the robustness. But also it helps, in fact, to show the challenges regarding the data requirements and how the performances can be viewed from the point of view of data. So another most important point in order to get this bridge between the experimentation and the industrial point of view of the performances is, as I said, the understanding of the system level requirements. So here we need to bridge the differences and the gap between the system level requirements and the AI level requirements, or even if you would like to call it the ML component level requirements. So from the system level perspective, we have some safety-related requirements that can represent the operational domain requirements, the performances, and also the operating conditions and the functional requirements. So those requirements needs to be cascaded to the AI level in terms of data qualities. Here in the project, we considered the representativeness and completeness that relates directly to the data management. And then the performances requirements for the AI model itself, which is represented more by too many features that we need to verify and to validate in the different steps from the learning management and the verification. So at this level, we need to identify at each development step what kind of cascaded requirements from the system level to the AI level that we need to make. Here we see the separation between the requirements identification and where these are located, and also what kind of verification do I need to verify or let's say to meet the objective of these requirements, such as minimizing the risk of some behavior of the AI model itself in order to get it implemented further. So focus. Oops, sorry. Yes, it's this one. Due to my phone. I always do these kind of mistakes. So, as I said, focusing on the AI level performances requirements. So to have a clear understanding of these requirements, we need to set the criteria for these requirements concerning the alignment with the system level objectives, having the requirements measurable and be able to be translated into measurable features of the AI itself, such as the accuracy, the precision, and all other kind of evaluation measures that we can use to validate the AI model, to be to have this verification of the AI requirements, and also from the perspective of robustness and the stability, and also the verification of the performances regarding the ODD. And if we can already identify some features from the system level and the target context where the model will be running, how we can include these elements in order to minimize the risk of losing too many performances after the model is deployed. So, putting all these together, as I said, we made this complete pipeline that implements the W-shaped learning assurance, where at each step we provided, in fact, several recommendations about tools and methods, requirements that need to be verified, the verifications, how to drive, in fact, the experimental evaluation in order to bridge these distances between the system level requirements and also the AI level requirements from the point of view of performances. So, let's have some words at each step, starting from the target application definition. So this part, which is more related to the first step of the W-shaped learning assurance, understanding the correlation between what we need to be developed at the AI level and what really meant on the AI, on the function or the sub-function of the system, let's say. Understanding the availability of the data set, its characteristics, having the performances influencing elements from the target domain, having a clear understanding of the KPI and the performances, how this can be translated into measurable and evaluable features, etc. And then in the second big part, this relates more to the whole W where the AI development is focused, including the data management, the learning management, and verification. So this one is built around twofold verification and let's say evaluation, the a priori evaluation and the a posteriori evaluation that are respectively made before and after the AI model training. So at the first loop of this process, the data qualification and preparation. So this can be split into three main objectives, having the identification of important criteria of the data quality and how we can verify them, staying again in a correlation with a big understanding of the ODD. And if by chance we are at the beginning of the project, we can have a maximum definition of the ODD. So this is the time where we need to identify the features for the data qualification. And then in the second big part, we will work on the model design and adaptation, taking into account the outcomes of the first red loop, and then perform the three big parts concerning the selection of the evaluation methods, the selection of the model architecture regarding the data, and also how we can project more in the future for the model, how we can split the data, how we can implement it, etc. And then on the third big part, so this is around the evaluation of the model itself. We expect the design of the model, the architecture, all these elements have been selected. So now we focus only on the development of the model itself, the training, getting back to the design of the model if needed, and what kind of verification. At this level, we should have all the KPIs translated into evaluation measures, and we can use them directly. And we need to make sure that the combination of the evaluation measures is correlated, in fact, with the requirements that we need to verify at the AI level itself. And then, at the fourth step. So here is a step back into the data qualification. So there were a question about redoing task 1 and 2 if we have some robustness problems after the presentation of Numanis. Yes, this is the time, in fact, where we need to get back to the data qualification, or even further, go again back to the ODD and understanding. If we are missing something, we developed the model, it is validated on the generalization evaluation, but getting into the after training evaluation and the verification just before the implementation, we see that the model is not good enough, or it is not stable, or it is not robust for some perturbation on the data. We should get back to the step that is more likely to bring better performances to the AI model itself, without forgetting that we need to change something. So this something that we need to change can be the data quality, the data volume, or the generalization evaluation, the bounds, the architecture of the model, too many things. We need to identify what is the most important criteria that have caused, in fact, this getting back. And then, if once the model have been validated, we can go into the implementation and verification, where at this stage, we need to verify that when the model is implemented in the target application, there is less or a minimum amount of error. So, or maybe this small error margin that we can have will be acceptable. There will be no impact on safety, or let's say there is some monitoring at the system level that can identify what the AI model wasn't able to identify. And if the business says, yes, I can accept it, so yes, we can implement the model. Otherwise, we need to get back again, and we need to identify what should be done better. Yes, I can go through this one. And then finally, once the model implemented, after the use of the model on the target system, here it is our understanding, in fact, and the logical way how we can monitor the model. So here again, it is a bit out of the scope of the MLEAP project, but it is really important for us to highlight this point, because once the model accepted and implemented into the target system, if there is at system level at some point some evolution on the needs, some evolution in the functions, or maybe having a larger ODD, having an adaptation of this system, but in a new area or a new context, we should verify that the model that has been already validated on the different steps from 1 to 5 is still usable, and also still meet the requirements from the AI perspective, the system perspective, but also having the intended behavior for the new system version. So, yes, I'm getting back. And I think I'm in the conclusions. So I still have time. Yeah, plenty of time. Okay, thank you. So now the most important conclusions, in fact, at this point, as I said, in order to have at the AI level, so the most important elements from the data, the ML modeling and the development, but also having the ODD understanding, the system level requirements. So these elements, these 3 points, are the main engine of having a good model and being able to say that the AI model that has been developed is accurate enough to be implemented in the target system. So the first conclusion regarding the data management and qualification. So there is the completeness and representativeness. So maybe for some of you, these 2 criteria are not enough, but just check the complete report. You will find that for the data completeness and representativeness, there is too many criteria that should be verified in order to check these only 2 points. There is the relevance, there is the amount of volume of data, there is too many features that relates to the completeness and representativeness themselves. So to guarantee this, we need to check again the ODD. I said, so having a complete definition of the ODD, it is imaginary. It is not possible for all use cases, but if it is possible for some reason, starting a new project to have this clear understanding and this complete definition, why not? It is a key of success for any AI project. And then another common recommendation between the whole tasks, and not only for the data management, it relates to the choices of the models, the methods and tools in order to verify, to evaluate some criteria. Here it is more focused on the data quality assessment, but it applies also for the generalization and the robustness evaluation. We need to target the measures that translate better the requirements from the AI perspective, but also the requirements that have been cascaded from the system level in order to have a complete and exhaustive evaluation of the AI itself, but the data also. Regarding the model design, the development, the generalization, assurance, and verification. So one of the most important conclusions relates to the use of tools such as the generalization bounds to have the guarantees, but it is not enough. As you can understand, after all the presentations of this morning, there is too many criteria related to the generalization of the model and also the robustness. It is not only about having one measure, but all the process matters. All the different steps, the choices that you can make at different development levels are important in order to guarantee or not that the model will be working well. And also having the alignment of the experimental and industrial objectives, I think this is one of the most important things. And finally, at the learning verification step, the performances, the robustness, the stability of the model. So this is again a key criteria in order to validate or not the model. So there is too many methods that have been tested, too many results shown, and there is too many discussions on the complete report. So you can find enough materials just to verify that at the learning verification step from the W-shape, you can be able to validate or not some criteria for the robustness and the generalization. So I think we have enough time for questions. Thank you.
Thank you, Thierry, for the presentation. So maybe we take two questions and then we continue with the EASA perspective on the MLEAP takeaways. And we will have plenty of time after the MLEAP takeaways for questions. We just take we're just taking two.
Okay.
So how have you demonstrated the sufficiency for purpose of the process controls you recommend? How do you know they confer to necessary confidence?
Xavier, tu veux en dire quelque chose?
I guess the question relates to the process you just presented. But like any process, what we've been doing in MLEAP is validating with use cases, toy use cases, and more complex use cases. It's a really good question. That's one of the challenge when you define development assurance techniques or learning assurance in this case. How to make sure that we have a sufficient coverage and that what we have is necessary. We have a set of reviews with experts. We have public consultations when we do guidance like the concept paper. If for this project we did not have the luxury of going through this type of public consultation because we had a 2 years period for the project. However, we receive also comments, we receive feedback that help us establish this process. Thierry, if you want to.
Yeah, and just continue.
Okay, so one more question. So I am still not seeing a straightforward answer for how to demonstrate the capacity for unintended behavior is adequately controlled. Can you please explain?
Okay, so for sure, because there is not a straightforward answer. It is a whole, in fact. You need to analyze the behavior of the AI model. What I mean by the behavior of the AI model, which means the performance regarding the measures that you have selected, the behavior of the learning step, the learning behavior of your model. Is it a model that tends more to overfit during the training, or during the training the performances are evolving in a good way? So having, let's say, some curves that go up and down during the whole training, it is not a good sign. If it doesn't go stable at some stage on the training, it means that the model is still overfitting. So if you put this one into the implementation, for sure, the behavior of the function as a whole and of the subsystem or the system that takes the AI part will not be acceptable. But at the system level, if you mean that at the system level, if there is some behavior that is not acceptable, so I think this is not only related to the AI part. So you should analyze, in my point of view, too many things related to the system level. It's not only at the AI part.
Okay, thank you, Thierry. So let's continue with the presentation on the EASA perspectives on MLEAP takeaways. So François, floor is yours.
Comment on fait là? Okay. Good afternoon, everyone. Thank you to all of you from the consortium for all these presentations. I think we had a very long journey, but when I look at all the results, even if we cannot conclude on everything, I think we progressed a lot during these 2 years. Even probably some of the concepts that we had at the beginning have evolved during these 2 years. When I look, for example, at representativeness of a data set, I think what I had in mind 2 years ago is not exactly what we have in mind now. So really great experience and great achievements. So for this presentation, Xavier will complement my few slides. I will start with some takeaways from this MLEAP project before we drive you through what will be our implementation plan from this journey. During all these presentations, the notion of ODD was repeated and repeated, and it confirms that we had in mind some time ago that the ODD is really the centerpiece of the learning assurance concept. First, it drives the data management process, first from a completeness and representativeness perspective, but not only. Second, it's an important element when we deal with the generalizability of the model. And also it is at the core of the requirements that will be linked to robustness and stability of the model. So definitively ODD is a cornerstone in the whole process, and probably that it was also a difficulty during our journey with MLEAP, because we were missing strong ODD from the start. From task one, I think we have a set of methods that have been tested first with tow use cases and later with aviation complex use cases. So we will have to guide whether these methods apply to, and now if we put that in perspective of the generic pipeline, we will have to clarify which of these methods better apply to the a priori evaluation and verification, and which one will mostly apply to the a posteriori evaluation. Second, we will have to also look at which of these methods better apply to low dimension use cases, and which one are more suitable for high dimensionality use cases like computer vision or audio or speech to text applications. And last, we will have to segregate between these methods the ones that really have a goal to identify a lack of completeness or a lack of representativeness, and the ones that could contribute to the satisfaction or the demonstration of rather good representativen's and completeness. I would also add that, and it was mentioned this morning, we also expect the research to invest in this domain. Probably there are some domains like generalization and so on where they are very active field of research, and probably this is an area that is a little bit poor with regards to research. Now from task 2, I think one of the main conclusion is that the set of methods which have been tested so far did not really allow to conclude with regards to complex and high dimensional use cases, and the ones that we have with in the aviation domain. So we will have to investigate other methods. However, generalization will be a key topic when we will extend the scope of the concept paper towards higher criticality application. I will just refer to DAL-B, DAL-A applications, which are not yet considered in the scope of the concept paper, but we for sure will have to go into that direction, and then generalization will be really at stake. So we really need to identify the means of compliance in this area. The good point is that this is a very active field of research, and we hope, we had a question, will it be in 3-5 years? I don't know, but we hope all that there will be some progress in the coming years with this regards. Discussing now about stability and robustness, I think it was very clear from the presentation that not one single point of view to address these particular properties will be enough. We will have to mix different methods, statistical methods, formal methods, empirical methods, all of them with their advantages, but also with their limitations. But for sure, we would expect our applicants to go into these different directions to demonstrate stability and robustness of the applications. A few words about the generic pipeline that was just presented. I think it is a very interesting element that was investigated during the MLEAP project. Okay, it introduces this notion of a priori and a posteriori evaluation and verification. When we look at it, in the context of the free tasks, we have also to look at its extension with regards to some other properties and some other objectives that we have identified in the concept paper. It has been elaborated and in the context of the free tasks, so with regards to data completeness, generalizability, robustness, but we have to consider this pipeline in the global context. And also for the applicants, they will have to look at how to integrate this pipeline into most probably the MLOps industrial processes that they have in mind or they have already implemented in their software factories. So this is also not the end of the journey. I would say that the generic pipeline proposes a way to look at generalization from a qualitative perspective, not yet from a quantitative perspective, but I think it's a very interesting element that we need to consider. This being said, I will pass the floor to Xavier.
A couple of slides on what we will do next. What is our implementation plan? Like any research project funded by the EU, we are also preparing the next steps. And well, we already took into account some of the results of MLEAP. The issue 2 of the concept paper took into account the result from the internet report. So in some places, in some means of compliance, you have some references to formal methods, for instance. And then the final report, published at the end of last month, is going to be used to refine our guidance material in AMC. But also what was mentioned earlier in the Q&A sessions, we have assessed a number of tools and methods. And it could make sense, like what we have seen in other domains, to have an R, SAE R, listing the methods and listing the advantages of some methods. So that could be an idea that we will submit in the future to EuroCAE. The priority in terms of action is to support, with the result of MLEAP, our actions and involvement in the Working Group 114. At the end or the beginning of next year, the ARP 6983 is going to be published. We are. I'm looking at you, Christophe. Is it correct? I hope so. Let's say it will be soon published, and we will. We have some material that is not only guidance material, but could also find its place in some industrial standard. The point is, it could be a good opportunity with this publication to come in the next month to see if some result of MLEAP could be used for the standard. A third version of the concept paper is foreseen by the end of next year. So we will, as we also explained earlier today, to take profit from this opportunity to update some means of compliance or some objectives based on what we learned during this validation exercise. MLEAP is, in a way, a 2 years validation exercise for EASA to test some objectives on real aviation use cases. So we've learned a lot through this project, and so some conclusion or some outcome of MLEAP will be used in updated the concept paper at issue 3. And then this rulemaking task on AI that was presented yesterday, that will last for the next 3 years. MLEAP will be like the IPC CODAN formula or other studies we've launched, one of our building block to support the rulemaking task. One particular slide on the use cases. What I explained this morning is that one aspect of MLEAP was to get some experience on actual models, datasets, tools and methods for EASA. We have a dedicated platform that has been set up by Airbus Protect that will stay available for the next 2 years. So for the next 2 years, we are able to rerun and to dig into some of the results. That's a really great opportunity for the team in EASA for the AI program. We also receive a set of artifacts that was part of the project. The consortium delivered to us a large amount of data, including models, scripts, some tools are available on the server. For what is public, we are assessing these days whether some of those examples, some of the methods that have been tested could be shared. There is a lot of material. We have more than 10 gigabytes of data that could potentially be published. The thing is, to publish something, we need to also provide a bit of support. So we would also value some feedback from some of you in terms of what you believe in MLEAP could be useful. So if you have some ideas, some projects where you think some of the material of MLEAP could be useful to you, we would be happy to discuss and see if we can make some material available. And then as a last slide for the day, what to expect with regard to the 3 tasks. Well, for task 1, we have a set of interesting recommendations and outcome in chapter 4 of the report. So we'll augment the existing means of compliance. Likewise, for chapter 5, that will be used for generalization aspects in the concept paper. We have also a set of recommendations in the pipeline that will be helpful for generalization. Robustness, we also have recommendation in the dedicated section of the final report, section 6. But we will also, as Arnaud explained earlier, there are some challenges with LM11 that has to do with the stability of the learning algorithm. Some of the experiments, as Arnaud has shown, were challenging to run. They were taking a lot of time. We have also some feedback from other stakeholders that it could be useful to assess whether this objective in the context of the other existing objectives. I believe the audience made a remark earlier today on whether the trade-off bias variance could also, in some aspects, or when we look at the trade-off bias variance, maybe there is some overlap with LM11. So maybe it's an area that could help us refining LM11. Relevance property that was shown in detail in the task 3 presentation seemed also promising. We've seen earlier today some interesting result on how, for a speech-to-text application, relevance could help explaining some of the results. But that's not something we consider today in the EASA concept paper. How to account for relevance will be also one of the topics in the coming months. And then further research. Well, we've not solved all these open questions, hard questions we had with MLEAP. We will have follow-up activities and R&D research activities in the AI program. Maybe not in the near future directly on those topics, but clearly there is some interest in having further research on task 1 and task 2 primarily. But EASA is not the only organization supporting research. In the past, other authorities like the FAA have published reports on visual landing. So we will be keeping an eye on what what other authorities are doing, and there are also external groups. You may have probably seen the deal paper published a couple of days ago or weeks ago on the feasibility of the EASA learning assurance objective. So there was a complete paper looking at the objective and the remaining challenges. We've been using deal material extensively in the concept paper. I was looking earlier today. I believe there is around 10 references in various places to some work of deal. And so clearly, other organizations outside of certification authorities are looking at some of the objectives we defined in the EASA concept paper. With this, I will open to questions on the conclusions.
Thank you, Xavier and François. So let's continue with the Q&A. So a question again from you, Stefan. So can you address it? It's on the screen.
But I have my doubts that we can use empirical verification on data-driven models, because empirical verification is what we do for standard simulation, for example, in the frame of structure analysis, structure and loads, panel 3. But can it be really accepted for data-driven model? That is a question.
Yeah, I would say that's an open question. I guess you raised this question when we were on task 3 earlier today.
Yeah, indeed.
Well, we've been back and forth on that. What we get from empirical methods is relatively. I mean, these methods are relatively easy to implement, but the level of confidence that you get is relatively low. So using empirical methods alone, I would say it's use cases dependent. But if we are dealing with a relatively complex or high dimension use case, I guess it will be quite challenging.
I agree.
Oh, yeah.
However, I think they can be very valuable to start with. But
like I said, I think for the very specific scenario where you have like a combination of really crazy factors that can occur to break the system, statistical method will have trouble finding those and generating those. Whereas empirical will say, at least look, we've done these scenarios and we have tested the system under those to see whether or not it breaks. But it will definitely never replace all the work done by statistical and formal.
Thank you. A question for you, Thierry. So system-level architectural and other mitigation are not new, nor they are ML specific. Are you saying that's the ultimate answer for the remaining gap?
Thank you for the remark. In fact, yes, it is not new and it is not ML specific, but it is one of the tools, one of the considerations in order to enhance and to get to bridge this gap between the experimentation and the industrial, and between the AI level requirements and the system level requirements. It's not only about the understanding the architectural mitigations, so the choice of the models regarding to the deployment platform and the type of the data that can be used. It is more than that. It is also related to the performances, to the monitoring that you have at system level, the monitoring that you have about the output of the AI component, how this output will be processed in another layer of the system. So if you say that an 95% of accuracy is enough because your monitoring handles it, so yes, it's good. But in another case, a 99% is not enough.
So this is not a question, but it's more of a remark. So following learning assurance rule and all good practices doesn't mean that at the end the model will fit performance requirements. Anything to comment about it?
I think it is a comment. It's true. Yes, AI is not magic. That's why, to complement the preceding question, yes, we need to take into account too many things. The data qualification, what are the criteria for the data qualification? And then the requirements, what kind of requirements I need to consider from the AI perspective, from the system perspective, and what are the influencing elements? How can I minimize the risk of losing performance after the implementation? It's the whole, in fact. It's not about having one function as a guarantee, as a magical thing. It's more about finding the good recipe for your AI model itself.
So aside from the data augmentation done on the training data set, generalization can also be done directly on the model, such as weight, penalty, dropout, etc.
Yes, of course, yes. And we did it. So we found it so obvious that it wasn't mentioned in the presentation, but you can find again in the report all the considerations that was used, in fact, for the model configuration regarding the changing on the hyperparameters. There is a nice figure showing the impact of the different choices on the hyperparameters and all of the values, the dropout, the non-dropout, the normalization, etc. So we found it just obvious. We haven't mentioned it on the presentation.
So do you have requirements for defining suitable ODDs and example of well-defined ODDs for aviation use cases?
I think we have no requirements. I think there are different use cases. For low dimension use cases, I think defining an ODD is not that difficult. Because at some point you will start looking at some data that you have collected. You will start running models. You will identify the features of this model. From the features, you will define progressively the ODD. And as it was presented, with the pipeline that is proposed, there will be iterations and iterations going back and forth from the ODD to the data collection to the model and so on. The difficulty is really when we are facing high dimensional use cases, like in computer vision, and in this case, defining the ODD is much more complex. But I think the pipeline that is proposed will help also defining the ODD, refining it, and progressively identify the parameters that really represent the ODD, and these parameters progressively will be used to identify the outliers, the edge and corner cases. They will be in support of the robustness requirements and so on. So I think there are no requirements. There are good practices, and I think the MLEAP project delivered a set of practices. And once again, I think the proposed pipeline will surely help.
Just to complement what's already said, I think there is not this magical recipe, but you have two magical ingredients, the AI expert and the business expert, because you need both of expertise in order to have these wider as enough definition of the ODD. So the expert on the domain, it's not only for aviation, this applies for all the use cases where you need AI. It's about understanding how the system works, what are the accepted things, and what is the available data, the nature of the data, etc., and the accessibility of the data. But also you need an AI expert, because this one will say if there is some correlation with the existing tools on the AI development or not. So we need to work jointly.
If I can add just one more, there is currently no document stating requirements on that, but there is currently a ballot and AC42 for project on ODD and domain definition to write requirements in EASA. So if anyone is interested, there is this place where you can help draft the first requirements on how to build a proper ODD.
So, okay, so another question for you. So how can people who are working directly in project deploying AI in the industry contribute to the roadmap, the guidance is then standard from EASA or EUROCAE?
For you, I can reply as you want. For the EASA AI program, we've been establishing and updating the roadmap based on industry feedback. And certainly some of the input and the discussion we have had through the various IPCs and this R&D project are helping us updating and making sure that our roadmap is aligned with industrial needs. For EUROCAE, I'm not the best person to answer.
Yes, as you said in the conclusion, it will be. We have been synchronized with people working on MLEAP during all the project, of course, but the outcome of this MLEAP project will be input for the EUROCAE. Of course, EUROCAE works on the future standard.
If I can add something to this on the possibility to contribute, you can also use all the occasion of public consultations when we update the concept paper and during the rulemaking process. That will provide us for sure valuable input at various stages of our processes.
So yesterday we discussed about AI and autonomy. So how does MLEAP affect AI and autonomy levels? Who wants to take this one?
I would say MLEAP is not affecting the AI autonomy level. It's two topics that are not related directly. MLEAP was really concentrating on the W-shaped process. The autonomy level are defined at the beginning of the guidance, and we don't have direct connection. This project was already 2 years long, looking already at 3 technical detail tasks. We had to choose the point of interest for this first AI program research project.
And maybe just to complement Guillaume speaking, actually, all levels, I mean, this applies to all levels. Just to make it, there is not a connection in terms of proportionality of the AI levels on the W shape and the learning assurance process, because it applies to absolutely every system, every level. So it's a very generic, let's say, contribution of MLEAP to any possible AI level. Yeah, thank you.
There is no specificity, but I don't foresee at this stage to make recommendation on updated the definition of the AI level from MLEAP.
So this one is for you, Thierry. So you've been talking all day about single models, not systems. So why do you confuse them?
I don't think we confused model and system, because we talked about the requirements at the system level. Yes, the requirements at the system level. What, for example, if you will embed an AI model just in the aircraft to detect, for example, the runway. So it is. I'm not gonna talk about the systems on the aircraft. I'm not that expert, but the AI model will be just the neural network, for example, that you will be embedding on it. So there is no confusion between the system and the model, and the considerations that we need to take into account from the AI level and the system level, these should be related between them. So if the person who asked this question is in the room, if you want to add a comment, don't hesitate.
So is MLOps a higher level objective and related to CO objective at the CP02? Can you please elaborate on that?
So when I referred to MLOps in the slides, I was referring to MLOps as an industrial process, like in the software, you could have Agile or DevOps. So for us, we refer to it because most of the applicants that we have facing us, we know that they put in place an MLOps industry state-of-the-art pipeline to develop ML models. So we don't have any objectives related to that kind of means that could be in place at each and every applicant. So no, there will be no objectives in the CO objectives related to MLOps.
Maybe we can take a question from the room. Yeah, up there. Thank you.
Maybe micro.
Yeah, actually, my question is in the list too. What about adding a use case with generative AI that would enable you to address the prompt engineering, chain of thoughts, and apply your pipeline on this type of use case?
So thank you for this suggestion. Yes, it is very interesting, but I will answer with another question. So does these use cases already industrialized today in aviation? So is it one of the priorities that have been put ahead on the real use cases? Is it embedded somewhere in an aircraft or not? So I think there have been some priority selecting the use cases, the data availability. So we targeted real things that are already used. Okay, and so in the MLEAP project, the scope was not for the generative AI. It was not. So the generative AI today on chain of thoughts, ChatGPT, all these kind of stuff, you have more than simple supervised learning models. You have the reinforcement learning, the transfer learning. There is too many kinds of machine learning ahead behind these models, these magical tools. And this could be a good point maybe to propose for the AI roadmap to be included, since generative AI is taking a very big march today on the industry. It is more and more used, even as mentioned yesterday by Guillaume. So it is kind of tools that helps the production, that helps other tools without putting them directly on the avionic use cases. But for MLEAP, it wasn't in the scope. So if you want to add this one, I think you will need 4 more years in order to reach all the objectives, because only for the generative AI, there is too many complexity that we need to consider.
Yeah, thank you, Thierry. I think you said the most of what I would have also mentioned. It's true that we oriented from EASA perspective the MLEAP use cases with what we had on the plate at the time where we started the project. So meaning really let's call it the embedded AI. This is really what we worked on as presented yesterday. Mostly so far, we start the rulemaking task, so we are progressing in this, let's say, in this stream. But there is a parallel stream growing, and thank you for your question again here on generative AI or AI in trustworthy tools. Let's put it like this. And this is something we aggregated in a project, as I mentioned yesterday. So more to come on that side, and possibly why not MLEAP, generative AI MLEAP? Why not? Clearly, when we have at least set the scene of let's call it the generic pipeline we see for this type of approaches. And after we can really dig into details, why not in another research project? Yeah. Thank you for the question.
Actually, Gen AI was not in scope, but it did not exist when we drafted. I'm a bit exaggerating, but it existed.
Don't you think that considering the complexity and the unknown everywhere, the focus should be on architecture that contains the unknown?
I think I will need more clarification on this question. I really don't understand what you mean by unknown and everywhere and focus on the unknown. Do you mean the out of the domain of definition, for example, for a data set or for any system handle specific cases? I'm sorry, I really don't understand the question.
Yeah, I mean, I don't know if the person is in the room, but we have a discussion about credit that you can take from architectural mitigation. Clearly, if you can have architectural mitigations that help reducing the safety consequences in case of erroneous behavior, that's something you can take into account. What we wanted to do with MLEAP is looking at cases where these architectural mitigation do not come into play, so that you have to do something. If architectural mitigation can be implemented, that's certainly something that can be taken into account. Actually, a couple of years ago, one of the conclusions from the first IPC was that we would probably need some architectural mitigations to achieve the highest level of reliability, let's say. And there were later on some publication assessing whether we could really have independent instances of neural network. And this is still very preliminary work, but I believe there was also a paper from Deal on that matter that shows that classical architectural mitigation are not working so well. So that's also why we keep concentrating on the AI itself. And if we can have architectural mitigation, yes, that's a plus.
If I can comment on that, we are talking a lot about design and validation, basically, but we haven't touched the monitoring of AI in operation. And there is a lot of work that has been done and currently still being done in order to detect, for example, when you're outside your DD. And some of the work by exploring, for example, how the system is, the AI component is reacting, allows at system level to detect that, well, your component now is not really trustworthy, so you should probably go into fail-safe mode, or I don't know, give back the hand to the user or whatever. But the monitoring aspect will definitely kick in when we are considering the system architecture and how the component itself should be monitored.
Okay, one more question. So I can meet the compliance burden for many AI applications without imposing any of this, and system level handles the rest. Why is this necessary?
First of all, I think this is because there is sets of means of compliance by the EASA that these are recommendations that you have to provide those means of compliance implemented, provide those guarantees, those verifications made. So I will let the EASA complement on this, why these compliance means of compliance exists. But for the AI component, yes, you can, from the experimental point of view, if you don't need to certify anything, you are working in a toy system, for example, you don't need a certification. Yes, for sure, you can have 100% of accuracy. You don't need to verify all the statements by the EASA, and you are satisfied with your system because you are not, in fact, putting into danger someone or somebody. So you don't need to do all these verifications.
Yeah. Yeah, the point, I mean, that's a good question. The thing is, if the system has no safety effect, well, you are even outside of the EASA concept paper. However, if you rely on some monitoring function, then you will have to demonstrate that this monitoring function is working and is fully covering the failure mode it's supposed to detect. And that may not be so easy for some application, especially if you have dynamic phenomena or rapid evolution of the output of the system, or I don't know what. So it's for sure, if you are outside of the concept paper, the objectives do not apply.
Okay, this is it for the questions. Time is up, so thank you, François.
Guillaume, if you want.
Thanks, Xavier, and Guillaume. Floor is yours. Maybe I go first. Okay. I can do that. Okay.
Maybe you do that, and then I will do the conclusions.
Okay, so like I said, so the event is now coming to an end. So let's wrap it up. So I want to thank you all for participating to this great two-day event. Thank you for sticking with us until the very end. I know it's been 2 intense days, but we have covered a lot of different topics and aspects. So thank you all for the great participation, whether online or here with us in the room. So I hope that you enjoyed as much the presentation as much as we did to present you them. So also, so it's been a real pleasure for the MLEAP team to being able to present the great work that was performed and done over the past 2 years. So now you have a real nice and great overview of all the main outcomes of the project. So congrats to the MLEAP team for achieving this great project and the great work that you've provided. I think they deserve a round of applause. And also, thank you, Guillaume. Thank you for the EASA for having us here 2 years in a row to present the great project that is MLEAP. Thank you for the great organization, and so big thanks to this. It's been once again a really good event. So they also deserve a round of applause. So just last but not least, so everything that was done over the past 2 years, so whether it's presentation, recordings of conferences like this one or like the other one that we did, reports, the 500 pages reports as well, if you want to read that one, or other ones, everything is on 2 main websites. So the primary website is the EASA MLEAP project page, where you will find absolutely everything that we have performed and done over the past 2 years, and as well as on the Airbus Protect MLEAP page. So on those 2 pages, there are also point of contact. So if you now have questions, you will be able also to address them directly to us. Should be names, either mine or the project manager on Airbus Protect side, which is Michel. And we will come back to you, and definitely if you can clarify or help on different topics, we will do. So the presentation, as I said at the beginning, will also be shared. Will be on those two websites. So thank you. This is it on my side. I will let Guillaume conclude. One more, yes. One more, yes.
I really want to thank all the contributors also from Airbus, but also on the consortium. So we made great work on this project, but we had also other team members that helped and contributed to the project. So not all the participants are here today, but we would like to thank them and thank also our digital department, the head of the digital department, Jeremy Bascon, that most of you know already. So he wasn't able to come with us to Cologne due to some constraints on the department. So we had, in fact, a great time working with all the EASA team. Thank you for your availability, answering all our questions and making this project a success. And also we would like to thank all the teams from Airbus that provided us with the use cases, with the models and the data sets that made also us able to verify the findings on real use cases. So that's it. Thank you.
Okay. Si tu veux dire un mot, Xavier, n'hésite pas. Dis un mot, il n'y a pas de...
I mean, yeah, if I may, it's been a real pleasure working with the consortium. I will not add additional person to the list to thank. Maybe all the legal department that gave us access. It was really a challenge, this part.
Thank you. No, thank you also from my side to Xavier and the team for this excellent MLEAP day. It was a promise last year that we would do something a bit more comprehensive, more technical, and going into the details of each task, and we made it. I know the day was dense, but the discussions were high up with the Slido and also in the room, so it worked very well. And I think, again, also many thanks to the full team to be here. It was not a given. You had an engagement really all over the project, and we have the full team here with us, your management, and it's really, really, it means a lot to us. So that was kind of a retrospective of day 2. If we go back to day 1, I will not do a retrospective more than Alain Leroy did very well at the end of the day, but very importantly, you could see from our side the strategy, what we achieved so far with the roadmap, where we go in terms of phases, the big word being consolidation. We'll not do again a presentation of what it means, but now you really have an idea. That means also a lot of interaction with all the stakeholders. That's the great thing of the EASA AI Days, that we can gather so many of you. I would say the full ecosystem, because we really have so variety of roles, profiles, and expertise, and that's a lot for us. We get a lot of feedback. From the feedback I got, I know that the day number 1 was very dense, and it was good to debrief over a beer yesterday evening. But concretely, next year we will try to think in terms of size. Of course, a number of topics came on top of what we initially planned. That's the nature of things. So possibly we can think about the size of the event to be with maybe half a day more. Let's think about it. So the perspective is to have an AI Days session and week next year as well. And I hope you will come numerous as you did today. You stayed really also for day number 2, and thank you as was relayed before. That's again very important, this interaction, this feedback. And that's one of the things I noted actually on the side of my notes here. We had through the feedback a lot of, let's say, we have a community. We need to activate this community even better than we managed to do it last year with, and the community has grown now. I've seen so many new faces and met so many new people. And this community, we have a lot for now, as you could see, of interaction with stakeholders, but possibly more in a one-to-one, except of course the working group, which is a wider spectrum. In consortium, of course, we have also several actors, but there are topics from all the discussions and feedback that gathers and several views, I would say, and we could, with the community of practice that we are building with these events, instead of waiting for next year to do the final report on what was said the year before, what has changed, what is the progress, and waiting for next year. It's important to do it, but before or even before we can engage on certain topics, creating some group of interest aside of the rulemaking group, which will be another opportunity, of course, to gather feedback, but maybe on certain topics. And I really noted what I would call trustworthy AI tools, generative AI. Let's put it in a kind of a package. We need definitely to clarify for all of you what are the expectations, what is kind of the pipeline, what are the big limitations, what are the difficulties, the risks, and then how do we get somewhere. And we have groups in the room, I would say, we are engaging with, and sometimes we don't have even enough time and resource to do it. So gathering smaller groups, but still, let's say, different views, I think would help us. I'm thinking also, Ines, about ethics. We discussed it at length yesterday. There is also a variety of views, a very wide angle of variety of views that could be extremely good to, instead of interacting one-to-one, to have really smaller groups that are bringing us further. So this is one of the things I think we need to think about for next year and before next year edition. Just checking my quick notes to not forget something. I was about to say, if you have any feedback on the conference, things you would like beyond what I was saying to improve over time, use the Slido. The Slido will be recorded. We will use as much as we can the questions that were parked and not answered. We cannot, in the timeline, answer everything, but you did a very good job today on the MLEAP side. We will try to answer them as much as we can on the website of the event. You will have all the presentations, the videos, but if you have further feedback, use the Slido right now. We will evaluate what has been said to make it even better next year. I think that's globally what I wanted to say. So many thanks. What I learned from today's final discussion is that we have several magical ingredients. We need now to create the final recipe to make it work. But as you all said, the recipe will be for one size. It's not a one size fits all. So there will be a recipe for supervised learning. We are very well engaged there, thanks to all what was said this week. There is reinforcement learning coming. There is symbolic AI. There is hybrid. There is generative AI, etc. So probably we have to really think still case by case, but genericizing as much as we can on the way. That's the strategy we have. And again, you fuel our roadmap effort, our roadmap implementation. So thanks so much for coming here. Have a safe trip back and see you next year at the latest and probably much before. Thank you.